Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the very fabric of reality itself. We're going to ask a deceptively simple question. What is almost everything made of? Are the smallest building blocks of the universe tiny particles, like little grains of sand? Or are they better understood as ripples in invisible fields that fill all of space? And how did science over the last century gradually assemble the standard model of particle physics, a kind of rule book for nearly everything that exists, while still leaving gravity, that most familiar of forces, as an unsolved puzzle at the edge of our understanding? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Imagine you're sitting quietly in a room, watching a chess game. You don't know the rules, you don't know which piece can move where, but you can see the players shifting their pawns and rooks across the board. Every so often, you notice something surprising. A piece jumps in a way you didn't expect, or the game seems to pause when you thought it should continue. This was how Richard Feynman, one of the most playful minds of the 20th century, described physics. He said it was like watching gods play chess. We can't ask them what the rules are. We can only watch carefully, notice patterns, and guess at the rules they must be following. Sometimes the moves make perfect sense. Other times, a strange exception appears, and that exception becomes a clue that there is a deeper principle we haven't yet uncovered. This metaphor captures the spirit of modern physics. For centuries, humans tried to explain the world by describing the pieces, the stones, the planets, the atoms. But what we really seek are the rules of the game, the hidden laws beneath the movements, and the story of the standard model, the theory that describes almost everything we can see and touch, is the story of how physicists gradually piece together those rules, move by move, from scattered clues. Let's begin our journey on this cosmic chessboard, not with the newest discoveries, but with the oldest urge of science, the desire to unify, to see not just separate pieces, but one underlying principle that holds them all. Centuries ago, forces seemed entirely separate. There was electricity, strange sparks that leapt from rubbed amber or a stormy sky. There was magnetism, lodestones pointing north, compasses guiding sailors, and there was light, the sun, the flickering of a candle, the glow of fire. These were different phenomena, mysterious in their own ways. But in the 19th century, a quiet revolution began. Michael Faraday, an experimental genius who had little formal education, imagined invisible lines of force stretching out from magnets and electric charges. He spoke of fields, a word that made people smile at first, as if he were talking about invisible meadows laid over empty space. But James Clerk Maxwell, with his gift for mathematics, took Faraday's intuition and wove it into 4 elegant equations. These equations showed something astonishing. Electricity and magnetism were not separate forces at all. They were 2 faces of the same coin, linked in an intricate dance. When electricity changes, it creates magnetism. When magnetism shifts, it creates electricity. And together, these changes ripple outward as waves, electromagnetic waves. And what are electromagnetic waves? They are light itself. The sunlight on your face, the glow of a lamp, the invisible hum of radio signals, the beams bouncing through fiber optic cables, all of it is the same phenomenon. Electricity and magnetism woven into one. Heinrich Hertz later built machines to make these waves deliberately, proving that Maxwell's equations were not just beautiful but real. Suddenly, light was no longer a mystery of fire or divine spark. It was understood as waves in a unified electromagnetic field. It was as though a chess player revealed that two seemingly different pieces, the bishop and the rook, were actually part of a single family of moves, connected by rules we had never noticed. This drive to unify has guided physics ever since. Each time we find that two forces, once thought unrelated, are actually part of a larger whole, it feels like a deep sigh of relief. The world becomes simpler, more elegant. But the chessboard does not stay still. Each simplification opens new puzzles. Just as Maxwell's unification of electricity and magnetism raised the question of what light really is, so later unifications would raise questions about matter itself. Is matter made of indivisible particles, tiny billiard balls bouncing in the void, or is it something more subtle? Could the things we call particles actually be ripples in invisible fields that stretch across the entire universe? For now, hold on to the image of that chessboard. Imagine the universe as a game whose rules are written in hidden ink. Sometimes we glimpse them clearly, like the unification of electricity and magnetism. Other times, we notice only anomalies, small discrepancies, subtle double lines in a spectrum, tiny shifts in numbers. But each clue, each anomaly, leads us closer to the deeper rules. Tonight we will follow those rules across a century of discovery. From Bohr's early quantum leaps to Dirac's prediction of antimatter, to the shimmering equations of quantum electrodynamics, to the electro-weak unification, to the strong bonds of quarks and gluons, all the way to the missing piece, gravity, that still eludes our grasp. The gods are still playing their game of chess. We may not yet know the full rulebook, but by watching carefully and by listening to the universe's quiet moves, we've begun to see the outline of something astonishing, a nearly complete description of everything we're made of. And with that, let us take our first quiet step into the quantum age. If you close your eyes for a moment and imagine the universe stripped of all its furniture, no chairs, no trees, no people, not even the stars, you might think of it as empty, just a hollow void. But physicists discovered that even what we call empty space is far from nothing. It is filled with invisible structures we call fields. They are like stage curtains you can't see, yet every actor, every particle, moves according to the folds and ripples in that hidden fabric. The idea of fields was not always obvious. In the early days, people thought of forces as direct pulls or pushes, one object reaching across the void to tug on another. Gravity was imagined as the Earth pulling on the apple, or the sun pulling on the planets. Electricity was sparks and shocks. Magnetism was the mysterious pull of the lodestones. All seemed different. Then came Michael Faraday, a man who worked as a bookbinder before becoming one of the greatest experimental physicists in history. Faraday was not fond of abstract equations. Instead, he thought in pictures. He saw invisible lines stretching out from magnets, like delicate spiderwebs crisscrossing the air. He imagined electric charges wrapped in a similar web. These were his lines of force. At the time, many scientists smiled politely at his sketches. It seemed fanciful. How could empty space be filled with invisible lines? But James Clerk Maxwell, a quiet genius from Scotland, took Faraday's sketches seriously. Maxwell translated them into mathematics, though tonight we will keep the mathematics in its softest form, like whispers rather than chalkboard hieroglyphs. Maxwell's four equations, as they are called today, told a breathtaking story. They show that electricity and magnetism are not separate forces at all. They are two aspects of one field, intimately linked. When an electric charge moves, it creates a magnetic field. When a magnetic field shifts, it creates an electric one. They chase and circle each other endlessly, like dancers bound in a duet. And when they do, their dance ripples outward as a wave, That wave is nothing less than light itself. Think of it. The sunlight warming your skin, the glow of a candle, the radio signals carrying music through the air, the Wi-Fi humming invisibly in your room. All of these are the same phenomenon. They're electromagnetic waves, the combined rippling of electric and magnetic fields. When Heinrich Hertz built a simple spark gap transmitter in the 1880s and produced radio waves in his lab, he confirmed Maxwell's vision. It was like watching a magician's sketch come alive. Suddenly, light was no longer an ancient mystery of fire or divine spark. It was the gentle vibration of a field, filling all of space. This was the first great unification in physics. Electricity, magnetism, and light revealed as one. A single rule hidden behind three apparently different pieces of the chessboard. And yet, like every move in Feynman's imagined chess game, this elegant step revealed new puzzles. If light was a wave, what exactly was waving? On the surface of the ocean, water molecules rise and fall. In sound, air molecules compress and expand. But what rises and falls in a beam of light moving through empty space? At first, scientists invented a hypothetical medium, the luminiferous ether, a kind of invisible jelly that filled all of space and carried the waves of light. But careful experiments showed no sign of such a medium. Light waves needed no ocean to travel through. They rippled in the fields themselves. Space, it turned out, was not empty. It was already structured, capable of carrying vibrations without needing any further support. The chessboard of nature had revealed another rule. Space is never truly blank. It is filled with fields that can stretch, bend, and ripple. For ordinary life, this may seem abstract, but pause and consider the lamp by your bedside. A quiet hum of electricity flows through its wires. Inside the bulb, electrons shake. As they accelerate, they disturb the electromagnetic field around them. That disturbance races outward at the speed of light, filling your room. When it reaches your eyes, it shakes the tiny receptors in your retinas, and your brain interprets the pattern as light. The glow you see is the ripple of a field that stretches from your bedside table to the farthest galaxy. But physics, like the chess game, did not stop there. The electromagnetic field was not the only one. Soon, experiments revealed the weak force responsible for radioactivity, the quiet disintegration of atomic nuclei. And deeper still, another field seemed to hold quarks together inside protons and neutrons, a field of extraordinary strength that would later be called the strong force. So the question grew, could these forces too be unified? Could electricity, magnetism, the weak force, and the strong force all be different patterns in a single fabric, like different melodies woven into one grand symphony? The dream of unification became a compass for 20th century physics. Each new discovery was measured not just by its novelty, but by whether it could be fitted into a broader pattern. Physicists longed to turn the cluttered chessboard into a single clean design. For us, drifting towards sleep tonight, the important thought is simpler. The world is not made only of objects, it is made of fields. Invisible, continuous, ever-present fields. The particles we talk about, electrons, photons, quarks, are not isolated beads rattling in the dark. They are ripples, excitations, brief disturbances in fields that fill the whole cosmos. When you listen to a violin, you do not focus on the wood or the strings, but on the vibration that fills the room. Particles, in this sense, are like those notes, fleeting expressions of something deeper carried by the hidden fields. So the next time you switch on a lamp or notice the warm brush of sunlight, remember that you are bathing in a field. Not a metaphorical one, but a real physical structure, invisible yet essential, stretching from your hand to the edge of the universe. And as we move onward in this journey, we'll see how these fields, when combined with the quantum rules of the microscopic world, give rise to all the particles and forces we know. Step by step, the chess game continues, and more of the hidden rulebook is revealed. Hello again, sleepy traveller. We've drifted from the chessboard of forces into the invisible presence of fields. But our story's only beginning, because once we start looking at matter on the tiniest scales, light itself becomes a guide, and it was light broken down into colours that led to one of the first great quantum revelations. Imagine shining light from a gas lamp through a prism, the way sunlight breaks into a rainbow. Instead of a smooth band of colours, hydrogen gas produces bright, sharp lines at very specific places. One of them is a deep, glowing red, called the H-alpha line. Others appear in blue and violet. These are not smears of colour, but razor-thin signatures, as if nature had written a secret code into the rainbow. For decades, these mysterious lines puzzled scientists. Why would hydrogen, the simplest of all atoms, emit light only at particular colours? If electrons were like tiny planets orbiting a nucleus, they should be able to radiate at any frequency, not just a few. Something was wrong with the planetary picture. In 1913, a young Danish physicist named Niels Bohr proposed a daring idea. Electrons, he said, could not move in just any orbit. They were confined to certain energy levels, like rungs on a ladder. To climb from one rung to another, an electron had to absorb or release a precise amount of energy. And when it released that energy, it appeared as a line of light with a very specific colour. It was a revolutionary claim. Energy itself was quantized, no longer continuous but delivered in discrete packets, like coins instead of flowing water. An electron in hydrogen could fall from the third rung to the second, and in doing so it would release a red photon, the H-alpha line that glows in laboratory tubes and distant stars. To picture this, imagine a child climbing a ladder in the dark. You cannot see the rungs, but each time the child steps down, you hear the creak of wood. The sound does not occur everywhere, only at certain intervals. In the same way, electrons step down energy levels, and each step produces its own note of light. Bohr's model explained the rainbow code of hydrogen beautifully. But nature, as always, held deeper secrets. When scientists looked closer, they found that some of those bright lines were not perfectly single. They were doubled, or shifted ever so slightly. The famous red hydrogen line was actually two lines, separated by a tiny difference in energy. This was called the fine structure. Such fine details could not be explained by Bohr's simple ladder. Something more subtle was at play. Enter Paul Dirac, an English physicist with a gift for equations that were as elegant as poetry. In the late 1920s, Dirac sought a way to combine two great ideas: quantum mechanics, which governed the atom, and Einstein's relativity, which governed space and time. His solution was a new kind of wave equation, one that described the electron not only as a particle, but as a creature with an intrinsic twist called spin. Dirac's equation did more than explain the fine structure of hydrogen. It predicted something astonishing. For every electron, there should exist a mirror twin with opposite charge. This was antimatter. At the time, it sounded almost absurd, matter that could annihilate ordinary particles in a burst of energy. Yet within a few years, the positron, the anti-electron, was found in cosmic rays. Dirac's poetry had spoken the truth. Pause for a moment and let that settle. From the faint double lines of a hydrogen spectrum, humanity uncovered the reality of antimatter. Tiny discrepancies in the rainbow whispered of an entire hidden half of the universe. To make this idea feel closer, think of standing at a piano. You strike what you believe is a single note. But with careful listening, you notice it is really two notes, very close together, beating against each other. That tiny difference tells you something new about how the strings are tuned, or even about hidden vibrations inside the instrument. The hydrogen spectrum is like that piano. What looked simple turned out to hide layers of structure, each demanding a deeper explanation. And so the ladder of light led us onward. Bohr gave us the rungs, Dirac gave us the fine details and the shadow world of antimatter. Together they transformed the atom from a miniature solar system into a quantum stage where particles dance to rules stranger than anything classical physics had imagined. There is something beautifully human about this journey. Scientists did not leap instantly to quantum field theory or the Standard Model. They followed faint clues, thin lines in the rainbow, slight shifts in colour, tiny anomalies that refuse to be ignored. It is a reminder that even the smallest detail in nature can open the door to vast new ideas. And it is also a reminder that light is not only illumination for our eyes, it is a messenger from the microscopic world, carrying the fingerprints of atoms across space. Every star you see at night is writing its story in spectral lines, coded rainbows that tell us what elements it holds and what processes burn within it. The universe speaks in colours, and our task is to learn the grammar. As you drift tonight, perhaps imagine yourself floating inside a great cathedral of light, each column painted with lines of colour. Some are bold, like the H-alpha red. Others are doubled, split just enough to hint at deeper truths. And in those delicate details, entire universes of theory and discovery await. Our next step will be to see how these discoveries, electrons confined to levels, antimatter predicted by equations, fit into a larger picture. Because soon the chessboard of nature would become crowded. New particles appeared, one after another, until physics found itself staring at a zoo of creatures that cried out for order. But that is a story for the next session. When you look at the night sky, most stars seem to shine with steady light. But if you pass that starlight through a prism or a telescope spectrograph, you discover something exquisite. The light is carved into thin, precise lines. Each line is like a musical note, telling you what elements the star contains. We already met the hydrogen alpha line, a glowing red signature from the simplest atom. Bohr's model explained its position. Electrons falling from one rung of the atomic ladder to another, releasing light of just the right colour. But when physicists built sharper instruments and looked even closer, they saw something unexpected. Those supposedly single notes were doubled. The red line split into two, separated by only a whisper of energy. It was as if the piano of the atom was slightly out of tune, revealing extra strings hidden behind the main ones. This tiny splitting, called fine structure, puzzled scientists. Bohr's ladder could not account for it. According to his picture, an electron's orbit should determine a single energy value. Where was this second line coming from? The answer lay in the nature of the electron itself. It was not just a tiny bead circling the nucleus. It carried an intrinsic property, something like an internal rotation, that we now call spin. Spin is not literally a particle twirling like a top, but a built-in quality that makes electrons behave as if they have an internal magnetic compass. This spin interacts with the motion of the electron around the nucleus, shifting its energy ever so slightly. That shift produces the doubled lines in hydrogen's spectrum. To describe this, physics needed more than Bohr's picture. Enter Paul Dirac, a mathematician whose equations were admired as much for their beauty as for their accuracy. Dirac combined quantum mechanics with Einstein's relativity, creating a wave equation that revealed the true nature of the electron. The equation naturally included spin. No extra assumptions were needed. It flowed directly from the mathematics. And then came the surprise. Dirac's equation predicted that for every electron there must exist a partner with opposite charge, the positron or anti-electron. It was the first glimpse of antimatter. At first this seemed impossible. Antimatter sounded like science fiction, a mirror world where particles carried reverse charges. But only a few years later, in 1932, a young physicist named Carl Anderson spotted tracks of these mirror particles in cosmic ray experiments. Tiny streaks curved through a magnetic chamber, showing that something with the mass of an electron but a positive charge had passed through. Dirac's bold prediction was real. From a doubled spectral line, the universe had revealed its hidden symmetry. For every piece of matter, there is a corresponding piece of antimatter. Think of standing at a mirror. You see your reflection, identical, yet reversed. If you lift your right hand, your reflection lifts its left. Antimatter is like that reflection, but not just in appearance, in charge and behaviour as well. And when matter meets antimatter, the two annihilate each other, vanishing in a burst of pure energy. This sounds violent, but it is also elegant. In that meeting, no fragments remain. Energy, in the form of light, is all that is left. In fact, this principle underlies technologies we use today. In hospitals, positron emission tomography, PET scans, use antimatter particles to map the living brain. Each tiny annihilation is recorded, building a picture of thought and blood flow. So, from the fine details of spectral lines, humanity discovered a hidden mirror of the world. It was a reminder of Feynman's chessboard. Sometimes the strangest new rules are revealed not by dramatic moves, but by small anomalies. The gods of physics, as Feynman might say, betrayed their secret in the faint doubling of a line of light. The notion of spin itself carries its own poetry. If you picture the Earth, it both orbits the Sun and spins on its axis. Electrons do something similar, but in a quantum sense. They have orbital motion around the nucleus and an intrinsic spin of their own. When these combine, the total energy shifts. That is why the hydrogen line splits. But unlike the Earth, the electron's spin is not mechanical rotation. It is more like an internal label, a quantum fingerprint that no two electrons can share in exactly the same way. The discovery of spin and antimatter deepened the sense that particles were not simple beads, but actors with layered roles. Each carried properties you could not see directly, yet those properties shaped the stage. The atom was no longer a miniature solar system. It was a quantum theatre, where particles obeyed subtle, hidden rules. If this seems abstract, imagine an orchestra playing in a darkened hall. At first, you hear only the main melody. Then, as your ear grows sharper, you catch the faint harmonies of instruments you had not noticed. The fine structure is like that hidden harmony, quiet but transformative. As you drift towards sleep, let that thought rest in your mind. The universe is generous with clues if we learn to listen closely. A single spectral line splitting into two was enough to point us towards spin, relativity and antimatter. Each discovery was not a giant leap, but a gentle step, guided by the faintest of signals. And in this way, physics crept forward, one whisper of light at a time. The chessboard grew more complex, the rules richer. Soon, however, the game would become crowded. Electrons and protons were no longer alone. New particles began to appear, discovered in cosmic rays and particle accelerators, until physicists spoke of a particle zoo. The tidy patterns of Bohr and Dirac were suddenly lost in a menagerie. It was time for a new way to bring order, to reveal deeper rules once again. That story awaits us in the next session. For now, you can rest with the thought that every star above you is singing in spectral lines, some doubled, some shifted, all carrying the quiet fingerprints of quantum mechanics. You are listening to the same harmonies that once led Bohr, Dirac and others to glimpse the invisible. If the story had ended with Bohr's ladder and Dirac's elegant prediction of antimatter, physics might have seemed complete. Hydrogen lines explained, electrons and protons in their places, neutrons discovered to balance the nucleus, and positrons confirming nature's mirror symmetry. It could have been a neat little tale. But the universe is rarely content with simplicity. In the decades that followed, particularly from the 1930s through the 1960s, physicists began to open windows into realms of higher energy. They built particle accelerators, giant machines that pushed tiny particles to near the speed of light and smashed them together. And they studied cosmic rays, high-energy messengers from space striking Earth's atmosphere. What they found was bewildering. New particles kept appearing. Mesons, strange baryons, muons, kaons. Each seemed to have its own mass, its own lifetime, its own peculiar decay patterns. Instead of a tidy handful of building blocks, physicists now faced a sprawling menagerie. It was as if someone had promised you a quiet farm with a few chickens and cows, and instead you walked into a carnival filled with exotic creatures, each demanding attention. The muon, discovered in 1936, was particularly famous. It looked just like an electron, same charge, same spin, yet it was more than 200 times heavier. I. Rabi, one of the pioneers of atomic physics, famously asked, "Who ordered that?" It was as if the universe had delivered a second electron without explanation, like receiving a duplicate set of keys for a door that doesn't exist. Other discoveries piled up. The pion, predicted by Hideki Yukawa to explain the strong nuclear force, appeared in cosmic ray experiments. Then came kaons, heavier cousins with strange decay patterns that introduced a new quantum label scientists simply called strangeness. The vocabulary of physics was beginning to sound less like mathematics and more like a bestiary. For everyday life, most of these particles were irrelevant. You would never meet a kaon while buttering your toast, nor would a pion pass through your teacup. But in high-energy collisions, these exotic particles blossomed for brief moments before decaying into more familiar matter. They were like fireflies in the dark, glowing briefly and then gone, yet their very existence hinted at deeper rules waiting to be uncovered. The abundance of particles created frustration as well as wonder. Without a clear pattern, the zoo seemed chaotic. Physicists longed for order, for a periodic table of particles the way chemists had once brought order to the elements. The task was enormous. Imagine walking into a cluttered kitchen drawer. At first you expect only forks and spoons. Instead you find whisks, can openers, garlic presses, and tools whose use you cannot guess. You try to arrange them. Some belong together, others don't. The mess seems endless. Yet somewhere in the chaos you sense there must be a hidden logic. That was the situation in mid-20th century physics. There were too many particles, too many decay channels, too many strange properties. But anomalies have a way of guiding science, just as tiny spectral splits once led to Dirac's equation. If nature offers you clutter, it is usually hiding a deeper pattern. Hints of order began to emerge. Murray Gell-Mann and George Zweig proposed, almost hesitantly, that all these hadrons, the protons, neutrons, pions, kaons, and many others, might not be fundamental after all. Perhaps they were built from smaller pieces. Gell-Mann called these pieces quarks, borrowing the name from a whimsical line in James Joyce's novel Finnegan's Wake. At first, quarks seemed like an abstract bookkeeping trick, a way to explain patterns without requiring the particles to exist physically. But as experiments grew sharper, evidence accumulated. Deep inelastic scattering experiments at Stanford in the late 1960s revealed that protons were not indivisible. Inside, they behaved like bags of point-like constituents, the quarks themselves. This was a moment of relief. The zoo was not endless. The menagerie of exotic beasts could be explained by combinations of only a few building blocks. Just as the countless molecules of chemistry are made from a small set of atoms, the countless hadrons were built from a small set of quarks. Quarks came in flavors, a playful term physicists adopted to make the concept easier to hold in mind. The first three were up, down, and strange. Later came charm, bottom, and top. Each quark had a fraction of electric charge. Up quarks carried plus 2/3 of a unit, while down quarks carried minus 1/3. Protons, for example, could be understood as 2 ups and 1 down, adding neatly to a charge of plus 1. Neutrons were 1 up and 2 downs, summing to 0. The strange quark explained the peculiar behaviour of kaons and other particles with strangeness. The pattern was beginning to clear. Still, new questions followed immediately. Why should quarks never appear alone? Despite decades of searching, no experiment has ever seen a solitary quark drifting freely. They always come bound into larger combinations. This puzzle would eventually be explained by the theory of quantum chromodynamics, where quarks carry a new type of charge called colour. But that chapter is yet to come. For now, what mattered was the sense of relief. The particle zoo was not a random carnival. It was a coded pattern waiting for its key. The key turned out to be quarks. As you lie here listening, perhaps picture the night sky again. For every twinkle of starlight, countless collisions of particles are happening within, producing brief showers of exotic quarks and hadrons. The universe, even in its most distant corners, plays the same game of construction and decay. Out of chaos, patterns emerge. Out of a zoo, a deeper order is found. The particle zoo reminds us of a gentle truth. Science does not always march directly towards simplicity. Sometimes it wanders into clutter first, but clutter is not a mistake. It is a doorway. In the next step of our story, we'll see how this doorway led physicists toward the revolutionary idea that particles are not tiny marbles, but ripples in fields. Quarks and leptons, photons and gluons, all excitations of deeper fabrics filling space. The chessboard was expanding, and the rules were about to become stranger still. Picture a quiet pond at dusk. The water is still, like a mirror. You toss a pebble, and circles spread outward, rippling across the surface. They are not new pieces of water. They are disturbances of something already present. This image, simple and familiar, is perhaps the closest we can come to imagining what modern physics tells us about particles. For a long time, we thought of particles as tiny marbles. The electron was a speck with charge. The proton was a lump at the heart of the atom. Light was imagined as either waves or little bullets called photons, depending on which experiment you looked at. But by the mid-20th century, a deeper framework emerged. It was called quantum field theory, and in this view, particles are not marbles at all. They are ripples. The universe, it turns out, is full of invisible ponds, fields that extend everywhere, filling all of space. The electron field, the photon field, the quark fields, and more. Each kind of particle is a ripple, a small disturbance in its own field. What we call a particle is simply the ripple travelling through space. This is not a metaphor scientists use lightly. The mathematics of quantum field theory really does describe particles as excitations, like ripples or vibrations. When an electron appears in a detector, it is not because a marble has flown through space. It is because the electron field spread across the universe has been nudged in such a way that a ripple passed by and deposited its energy there. In some ways, this is a startling shift. It means that what we think of as matter is inseparable from space itself. There is no such thing as a lonely electron floating in a void. There is only the electron field, and the ripple we call an electron is never apart from it. To feel this, imagine lying on a trampoline. When someone jumps, the whole fabric shivers. You may feel the disturbance even if the jumper is on the far side. In the same way, the fields of the universe are continuous fabrics, and the particles are the tremors that pass through them. This perspective also explains something curious: why particles can appear and vanish as long as the rules of energy are respected. Just as ripples on a pond can rise and fade without removing any water, so particles can be created or destroyed as ripples come and go. Matter is not fixed stuff but dynamic, flowing patterns. Now, not every ripple is one we can see. Quantum field theory allows for fleeting disturbances, what physicists call virtual particles. These are ripples that flicker for a moment and then vanish before they travel anywhere. They are like tiny waves that rise and collapse before reaching the shore. Though invisible to us, their presence influences the real world. They shift the energy levels of atoms, tilt the behavior of electrons, and subtly alter the properties of space itself. You may never notice, but your very chair is supported by this dance. The reason atoms resist being squeezed together, the reason your body does not fall through the seat beneath you, is that electrons in the surrounding fields exchange virtual photons, invisible quanta of light that act like messages passed back and forth. They tell each electron, stay apart, keep your distance. Without these constant, unseen ripples, solid matter would collapse. You're floating in a sense on a cushion of virtual exchanges. It is tempting to ask, are these particles real or just mathematical tricks? The answer is both delicate and profound. We do not see them directly, but their effects are measured with astonishing precision. They are part of the fabric of reality, part of the hidden game of chess. The gods, if we return to Feynman's metaphor, are not only moving the pieces we can see, but also shifting invisible pieces we cannot. Quantum field theory is not an easy picture to hold in the mind. Our everyday world trains us to think in terms of objects, apples on a table, stones in a stream. But physics invites us to soften that image. Think instead of melodies. A violin string, when plucked, produces not a lump of sound but a vibration in the air. That vibration carries energy, it can travel, it can be detected by your ear. In the same way, an electron is not a lump but a melody in the electron field. Once you begin to imagine the universe this way, even empty space feels alive. You may sit in a dark room thinking you are surrounded by nothing. But according to quantum field theory, you are immersed in a sea of fields, each capable of rippling, each vibrating quietly in the background. Physicists sometimes call this the vacuum, but it is not nothing. It is a restless stage, humming with potential. The next time you place a hand on your desk, remember that you're not touching solid marbles of matter. You're feeling the collective firmness of ripples in fields, stabilized by exchanges you will never see. The wood grain beneath your palm, the air around you, even your own skin. All are ripples on invisible ponds. It is a picture at once humbling and strangely comforting. We are not separate from the fabric of the cosmos. We are its ripples. Each breath you take, each thought in your mind is part of the great wave play of fields that fills the universe. And yet, this beautiful picture brings puzzles of its own. These virtual ripples, though invisible, sometimes leave measurable fingerprints, small shifts in atomic spectra, or the tiniest tilt in an electron's magnetism. To explain them, physicists had to push quantum field theory further, learning how to calculate with infinities and tame them into precise numbers. That challenge will guide us into the next chapter. For now, you can drift with the thought that the universe is less like a box of particles and more like a vast pond at twilight, where every atom, every photon, every quark is a ripple across its surface. Even silence is alive with possibility. If particles are ripples in fields, then the quiet background of reality is never still. Even when you think nothing is happening, the fields are alive with flickers, tiny disturbances that appear and vanish almost immediately. Physicists call these fleeting ripples virtual particles, but that phrase can be misleading. It makes them sound like simulations in a video game, when in fact they are as real in their influence as the furniture in your room. You cannot bottle a virtual particle or point to one with a microscope, but you can measure their fingerprints. One of the most famous came from an experiment in the late 1940s. Two young physicists, Willis Lamb and Robert Rutherford, were studying hydrogen atoms with microwaves. They expected to find energy levels exactly where theory predicted, but instead they found a small shift, a line that was displaced from where it ought to be. This became known as the Lamb shift. It was as though the neat ladder of energy levels we met earlier in Bohr's model had been nudged ever so slightly by invisible hands. Where did the nudge come from? The answer was the constant buzzing of virtual particles. The electron in hydrogen was not circling in isolation. It was surrounded by a cloud of momentary photons, tiny quanta of light that flickered in and out of existence. This cloud subtly altered the electron's environment, shifting its energy by just enough to be measured. At first, this seemed like a minor correction, almost an annoyance. But the Lamb shift proved that virtual particles were not a mathematical curiosity. They were part of the real stage play of the atom. Their dance had consequences, and careful ears could hear their footsteps. Another striking fingerprint came from the magnetic nature of the electron itself. Every electron acts like a tiny bar magnet, pointing north or south depending on its spin. If the world were perfectly simple, its magnetic strength should have matched the prediction of Dirac's beautiful equation exactly. But in 1947, physicists measured a small discrepancy. The electron's magnetic field was slightly stronger than expected. Physicists describe this difference in terms of a number called the anomalous magnetic moment. Today it is often written as G-2. We won't use the symbol, but you can imagine it as a tiny correction, 1 part in 1,000. This might sound trivial, but to scientists it was breathtaking. The only explanation was the influence of virtual particles again. The electron was never bare. It was dressed in a coat of fleeting photons, and at higher energies, even pairs of virtual electrons and positrons. This coat changed its magnetic personality just enough to tilt the number. And when calculations caught up with the experiments, the agreement was astonishing, matching to more than 10 decimal places. No other theory in all of science has ever achieved such precision. Think about that for a moment. Invisible flickers in a field, rising and vanishing in less than a trillionth of a second, shift the magnetic strength of an electron by a few parts per thousand. And yet, when we measure it, the match between theory and experiment is exact to the width of a hair compared with the size of the Earth. That is how faithfully quantum electrodynamics, the theory of light and electrons, describes the universe. Virtual particles are also the reason you're sitting comfortably right now, without sliding through the floor. The electrons in your body and the electrons in the chair beneath you repel each other, because they are constantly exchanging virtual photons. Imagine two people passing invisible notes back and forth at lightning speed, each note saying, "Keep away." The result is a cushion of resistance that prevents the atoms in your body from merging with the atoms in the chair. You are levitating in a very real sense, on an endless exchange of invisible messages. This image may seem strange, but it is what keeps the material world from collapsing into a single dense lump. The firmness of wood, the solidity of stone, the texture of fabric, all of it rests on the tireless work of virtual quanta, whispering, "Keep your distance," billions of times per second. If you would like another anchor, think of a crowded train carriage. People stand shoulder to shoulder, each shifting slightly, exchanging glances and subtle signals. No one is shouting or pushing, but the quiet communication keeps a delicate balance of space. Virtual particles are those silent signals, invisible yet essential. These tiny corrections, the Lamb shift, the anomalous magnetic moment, the firmness of matter, were not things anyone could have guessed from first principles. They were surprises, anomalies, like the unusual chess moves Feynman once spoke of, and each one forced physicists to refine their understanding, to admit that reality is not smooth and silent, but frothing and restless, even in the apparent calm of the vacuum. As you drift tonight, you might think of the air around you, which seems still but is filled with molecules darting in every direction. Virtual particles are even more subtle. They live not in air but in the quantum fields themselves. They are the tremors of the stage on which reality plays out. And though they exist only for a fleeting instant, their combined influence shapes the world in ways we can measure with exquisite precision. The lesson is quiet but profound. Absence is never empty. Even nothing hums with possibility. The chair you sit on, the atoms in your breath, the light from a distant star, all are gently nudged and sustained by the unseen ripples of virtual quanta. In the next step of our journey, we'll face a deeper puzzle. When scientists tried to calculate these quantum effects more fully, they found infinities leaping from their equations, numbers that blew up into nonsense, threatening to wreck the whole elegant picture. How could the universe work so perfectly while the mathematics seemed to collapse? The answer came from a new method, a way to tame infinities into useful predictions, a process called renormalization. But that, like all good stories, we will unfold slowly. By now, you might feel the elegance of quantum fields, ripples in invisible ponds, particles as excitations, and virtual quanta flickering in and out, leaving measurable fingerprints. It sounds beautifully coherent. And yet, when physicists first tried to calculate these effects in detail, they encountered something deeply unsettling. Their equations produced infinities. Imagine you are trying to balance your household budget. You add up your expenses, your income, your savings, and suddenly the numbers explode into infinity. That is not just inconvenient, it is meaningless. In physics, infinities meant the theory had gone off the rails. One of the worst cases appeared when physicists tried to calculate the influence of virtual particles around an electron. The mathematics suggested the electron's charge and mass should both be infinite. Clearly, no one had ever measured an electron of infinite weight or infinite repulsion. Nature itself seemed perfectly finite, precise to many decimals. But the mathematics screamed nonsense. For years, this was a source of despair. Some wondered whether quantum field theory, as beautiful as it appeared, was fatally flawed. Others pressed on, convinced the infinities must be hiding a deeper trick. The breakthrough came in the 1940s, during and after the Second World War, when a handful of physicists, Julian Schwinger, Shinichiro Tomonaga, Richard Feynman, and Freeman Dyson, each brought new ideas. Their solution was something called renormalization. The word itself sounds dry, but the concept can be softened. Renormalization is like cleaning up messy books. Imagine your household budget again. You discover you have accidentally double-counted certain costs, or lumped some expenses into the wrong category. By reorganizing the accounts carefully, you can sweep the infinities into redefinitions of quantities you can actually measure, like the observed mass and charge of the electron. What remained, after this careful bookkeeping, were finite numbers. Numbers that matched experiments with breathtaking accuracy. Richard Feynman, with his characteristic playfulness, gave the process an intuitive picture. He introduced diagrams, little sketches showing particles meeting, scattering, and exchanging virtual quanta. Each diagram represented a term in the calculation. Alone, many of these terms still led to infinities, but taken together and renormalized, they combined into precise predictions. Feynman diagrams became more than a tool. They became a language, a way of sketching interactions with chalk on a blackboard or pen on a napkin, turning the invisible play of quanta into something a physicist could doodle during coffee. And yet, beneath the play, the accuracy was staggering. The most famous test of this came with the anomalous magnetic moment of the electron, the G-2 number we met earlier. With renormalization and Feynman's methods, physicists calculated its value to 10 decimal places. Experiments matched digit for digit. Imagine predicting the distance from New York to Los Angeles and getting it correct within the width of a human hair. That is the scale of accuracy quantum electrodynamics achieved. This triumph was more than technical, it was emotional. The infinities had felt like a betrayal, as though nature had teased us with beauty and then slammed the door with nonsense. Renormalization reopened that door, revealing not only coherence but precision beyond imagination. Of course, not everyone was comfortable. Paul Dirac, the father of the relativistic electron equation, once called renormalization ugly. He disliked the idea of sweeping infinities into definitions, even if the predictions worked. To him, it felt like clever accounting, not deep truth. But others, including Feynman, saw it differently. Nature, they argued, had given us a method that worked, and its beauty lay not in its neatness, but in its success. Here is a gentler way to picture it. Think of a painter working on a canvas. Up close, the strokes may look chaotic, even sloppy. But when you step back, the picture is clear and luminous. Renormalization is like that. The close-up details may be messy, but the big picture is accurate and astonishing. For us, listening in the quiet of the night, the main idea is this. Quantum electrodynamics, the theory of light and electrons, survived its encounter with infinity. It emerged not broken, but reborn as the most precise theory humans have ever created. Every time you turn on a light bulb, use a phone, or watch a screen glow, you are surrounded by technologies that rely on its predictions. You may never need to think about infinities when you boil water or charge your laptop. But behind the scenes, the world behaves with a consistency that only renormalization made possible. It turned wild mathematics into gentle agreement with experiment. As you drift tonight, imagine balancing a checkbook that had exploded with errors, only to find with patient reordering that every cent is accounted for. Or picture a storm of ripples on a pond, chaotic and overlapping, that suddenly settle into a perfect pattern when viewed from the right angle. That is what physicists achieved with renormalization. The universe is not free of puzzles, but here at least, it whispered its rules clearly enough for us to follow. The electrons, magnetic tilt, the Lamb shift, the firmness of matter, all fell into place under the umbrella of renormalized quantum electrodynamics. This chapter of the chess game ended in triumph, but the game was not over. There were still other forces to explain, forces weaker than electromagnetism, forces responsible for the quiet decay of particles and the mysterious absence of antimatter around us. In the next stage of our journey, we will turn to that whisper of a force, so feeble it rarely shows itself, yet so fundamental it helps shape the very universe, the weak interaction. If electromagnetism feels like a confident voice, strong, bright, shaping light and electricity, then the weak force is more like a whisper. It is subtle, almost shy, and for centuries it remained hidden in the shadows. And yet, this quiet force has shaped the universe in profound ways, from the glow of the sun to the very balance of matter in your body. The weak force first revealed itself in radioactivity. In the closing years of the 19th century, Henri Becquerel noticed that photographic plates fogged when placed near uranium salts. Marie and Pierre Curie soon uncovered new elements like radium that glowed with this strange energy. Atoms, which had seemed stable and eternal, were actually capable of crumbling. This crumbling, known as beta decay, involved electrons being expelled from nuclei. But where did those electrons come from? They were not sitting inside the nucleus, waiting. Something inside was transforming, one particle changing identity into another, and releasing an electron in the process. For a time, the books of physics did not balance. Energy seemed to vanish in these decays. A nucleus would spit out an electron, but the total energy of the system did not quite add up. Some worried that perhaps one of nature's deepest rules, that energy cannot be destroyed, was under threat. It was Wolfgang Pauli, a thoughtful and sometimes anxious theorist, who offered a daring solution in 1930. He suggested there must be another particle, invisible and nearly massless, slipping away during beta decay and carrying the missing energy. He called it a neutron at first, but later, when James Chadwick discovered the actual heavy neutron, Pauli's invisible ghost was renamed the neutrino. Enrico Fermi built a full theory around it, and the weak interaction was born. The neutrino was elusive. For decades, no one could catch it. It interacted so rarely with matter that billions pass through your body every second without leaving a trace. They stream out of the sun, born from nuclear reactions at its core, filling space like a silent rain. And yet, despite their ghostly nature, neutrinos preserve the balance of energy, making sure the cosmic books are never cheated. The weak force is unlike its siblings. Electromagnetism has an infinite reach. The light from a star can travel for billions of years across space. The strong force, though, confined to the scale of nuclei, is immensely powerful, binding quarks with a grip that cannot be broken. The weak force, by contrast, is feeble and short-ranged. It can only act across distances smaller than the size of a proton, and its strength is far less than that of electromagnetism, and yet without it, the universe would be unrecognizable. The weak force allows neutrons to turn into protons, or protons into neutrons, processes that power the nuclear furnaces of stars. Without that whispering transformation, hydrogen would not fuse into helium, the sun would not shine, life would not exist. In time, physicists realized that this mysterious force must be carried by its own set of particles, much as electromagnetism is carried by photons. These new carriers were named W and Z bosons. The W particles, one with positive charge and one with negative, are responsible for processes like beta decay. The Z particle, electrically neutral, handles invisible exchanges, passing momentum without sparks of light. But here a new puzzle appeared. Why are these weak force carriers so heavy, while the photon, the carrier of light, has no mass at all? If photons are nimble dancers, gliding freely across the universe, then the W and Z bosons are lumbering giants, so heavy they can barely take a few steps before collapsing. Their mass is what makes the weak force so short-ranged, so feeble compared with electromagnetism. This difference cried out for explanation. How could two forces be so similar in spirit, both involving exchanges of particles, yet so different in outcome? Was there a hidden unity between them, like the unity Maxwell revealed between electricity and magnetism? By the middle of the 20th century, theorists began to suspect exactly that. The weak and electromagnetic forces might be two branches of a single tree split apart by some deeper mechanism. If that were true, then photons, W bosons and Z bosons would all be family members, their differences arising only because of the environment of the universe itself. But for now, the weak force remained a whisper, faint and puzzling. It had revealed itself only through anomalies, the fogging of photographic plates, the odd imbalance of energy, the sudden presence of ghostly neutrinos. And yet, like every anomaly before it, these whispers were clues, guiding science toward a greater unification. To hold this in your mind, imagine a family dinner. Everyone is speaking, voices overlapping, plates clinking. Then one person leans over and whispers just a few words, and suddenly the whole table shifts. People change their seats, food is passed in a new direction, the mood changes entirely. The weak force is like that, a faint whisper that can rearrange the fate of stars. Tonight, as you rest, you are bathed in the evidence of this force. Neutrinos stream through your body, born in the nuclear fire of the sun. You do not feel them, you cannot stop them. But they are there, silent travelers, connecting you directly to the heart of a star. The universe is full of such whispers. They may seem feeble, but in their quiet persistence they shape everything we know. And as our story continues, we will see how those whispers joined with light itself, revealing yet another layer of unity in the grand game of physics. The weak force, as puzzling as it seemed, carried a whisper of something grander. If the carriers of light, the photons, were massless and free to race across the universe, while the carriers of the weak force, the W and Z particles, were massive and sluggish, perhaps they had not always been so different. Perhaps, long ago, they were united. This idea became clearer in the 1960s, when several groups of theorists worked toward the same vision. They suspected that electromagnetism and the weak force were really two faces of a single interaction, the electro-weak force. But to make this theory work, they needed a mechanism to explain why one branch gave rise to a nimble, massless photon, while the other branch produced the heavy W and Z particles. The solution came from a field that had been hiding all along, one that fills the universe invisibly. It is now called the Higgs field, after Peter Higgs, who was among the physicists who described it. This field is unlike the electromagnetic field or the strong field. You cannot turn it on or off. It is woven into the very structure of space itself. To understand what it does, imagine skating across a rink. On one side, the ice is perfectly smooth, and you glide effortlessly. On the other side, patches of invisible syrup have been spilled. As you pass into those regions, your motion slows, and you feel as though you are dragging weight. In the same way, particles moving through the Higgs field experience resistance. Some, like the W and Z bosons, are slowed so much that they appear heavy. Others, like the photons, slip through untouched, remaining massless. The Higgs field breaks the symmetry. On paper, the electroweak force looks like one elegant whole, but in practice, the presence of the Higgs field differentiates the family members. It gives mass to some particles while leaving others light and free. This is why the weak force is weak and short-ranged, while light travels effortlessly across the cosmos. It's important to note that physicists did not invent the Higgs field simply to patch a hole. They were following the logic of symmetry. In the language of physics, symmetries are guiding principles like hidden harmonies. A symmetrical rule might say all directions are equal, or all particles of a certain type behave identically. But sometimes symmetries are hidden by the environment. Think of a perfectly round hilltop covered in snow. At first, every direction down looks identical, but the moment a skier pushes off, the symmetry is broken, one direction is chosen, and the landscape takes on a particular pattern. The Higgs field plays a similar role. It tilts the landscape of the universe, choosing which particles gain mass and which remain massless. Without this tilt, matter as we know it could not exist. Atoms would not form, chemistry would not arise, and stars would never ignite. For decades, the Higgs field was an invisible idea, a theoretical necessity. Physicists spoke of it with reverence, but also with frustration, because no one could prove it existed. If it was real, then there should be a particle associated with it, the Higgs boson. This particle would be a ripple of the Higgs field itself, a brief vibration we could, in principle, detect. But the energy required to shake the Higgs field hard enough to reveal its ripple was immense. For half a century, experiments fell short. Meanwhile, the theory worked beautifully. The electroweak model, with the Higgs mechanism built in, predicted phenomena that experiments confirmed: the existence of the Z particle, the rates of certain decays, the very pattern of the weak force. But without the Higgs boson, the picture was incomplete. It was as if you had deduced the presence of wind from the way trees bent, but had never felt the breeze directly. At last, in 2012, at the Large Hadron Collider near Geneva, the Higgs boson was discovered. Two great detectors called ATLAS and CMS each saw the telltale signs of a new particle with a mass about 130 times that of the proton. The announcement was met with cheers, tears, and champagne. Decades of patient searching had finally brought the invisible into view. To place this in a more human anchor, imagine you are searching for a friend in a crowded city. For years, you only see traces, footprints in the snow, a coat left on a bench, a reflection in a window. You're certain the friend is there, shaping the world around you, but you never meet them. Then, at last, one day, you turn a corner, and there they are. That was the moment physicists felt in 2012. The Higgs boson, the ripple of the Higgs field, finally revealed itself. The Higgs field is not something you can turn on or off with a switch. It has been part of the universe since the earliest moments after the Big Bang. Without it, the particles of the standard model would race around massless and chaotic. With it, they settle into rolls, acquire weight, and allow matter to exist. It is the invisible molasses that gives substance to the world. As you rest tonight, you might picture yourself skating across that rink, feeling the invisible syrup beneath the surface. Some skaters glide without resistance, others sink slightly, slowed by the drag. This quiet, unseen field is what gives your body mass, what allows your bed to press down beneath you, what lets the earth itself carry weight. The Higgs is not somewhere else. It is here, everywhere, silent but essential. The discovery of the Higgs boson was not the end of the story, of course. It raised new questions. Why this mass and not another? Why does the Higgs field exist at all? But for now, it stands as one of the crowning achievements of modern physics, a confirmation that the whispering weak force and the bright voice of electromagnetism truly share a common root. The Higgs field offered an elegant answer to the mystery of mass, but elegance on paper is never enough. Physics, more than any other science, is haunted by the demand for proof. Equations can be beautiful, theories can be tidy, but unless nature herself nods in agreement through experiment, the story remains unfinished. By the 1970s, the electroweak theory had become a confident framework. It predicted not only the existence of the Higgs field, but also the presence of heavy force carriers, the W bosons, one positively charged and one negatively charged, and the neutral Z boson. These particles were unlike anything seen before. They were heavy, about 90 times the mass of a proton, and they were fleeting, decaying almost instantly. To find them, scientists would need colliders powerful enough to shake the vacuum into producing such massive quanta. But before the heavy carriers themselves could be discovered, there was a subtler test. The theory predicted that the neutral Z particle would allow for a new type of interaction called a neutral current. Unlike the charged W bosons, which clearly altered particles by changing their identities, the Z would act invisibly, exchanging energy without producing electric charge. Detecting such a ghostly effect was no simple task. In 1973, at CERN in Geneva, researchers observed the first signs of these neutral currents. Neutrinos, those ghostly visitors from the sun and reactors, scattered in ways that betrayed the presence of the Z. It was like watching a breeze stir the curtains when the window seemed closed. The theory had spoken, and experiment had answered with a quiet yes. Still, the crown jewels were the W and Z particles themselves. To see them directly required extraordinary machines. In the early 1980s, Carlo Rubbia and Simon van der Meer led an effort to repurpose CERN's superproton synchrotron, a ring more than 6 kilometers in circumference. They used ingenious techniques to collide beams of protons and antiprotons head-on, focusing enough energy into a single point that the heavy W and Z bosons could briefly flash into existence. In 1983, after months of painstaking work, the signals appeared. Events in the detectors showed the unmistakable footprints of the massive carriers. First the W bosons, then the Z. There was no doubt. The particles predicted by the electroweak theory were real. The celebration was immense. Within a year, Rubbia and van der Meer were awarded the Nobel Prize. For physicists, this was more than a discovery. It was a vindication. The unification of electromagnetism and the weak force was not a fantasy. The chessboard had revealed its hidden pieces, and the rules matched the ones written in the theoretical playbook. Yet even with this triumph, one figure remained elusive: the Higgs boson, the ripple of the field that gave these carriers their mass. Decade after decade, experiments searched for it. Smaller colliders came up empty. The Higgs seemed to hide just out of reach, like a shy actor refusing to take the stage. Finally, with the building of the Large Hadron Collider, a machine spanning 27 kilometers beneath the French and Swiss countryside, the energy frontier was reached. In 2012, two giant detectors, Atlas and CMS, announced their results. They had seen the telltale signs of a new particle with a mass about 130 times heavier than the proton. The Higgs boson had been found. The announcement was met with standing ovations, tears of relief, and champagne bottles popped open in crowded lecture halls. For scientists who had devoted their entire careers to this search, it was a moment of profound human joy. Decades of calculations, predictions, and patient building of machines had culminated in a single confirmation. The invisible molasses of the Higgs field, long suspected, had finally revealed its ripple. For those outside the laboratories, the excitement can be compared to completing a massive puzzle. Imagine a jigsaw puzzle spread across a table, thousands of pieces arranged into a landscape. For years, the picture has been clear enough, but one stubborn piece, the final corner, is missing. The puzzle works without it, but the absence nags at you every time you look. Then, one day, you find the missing piece under the couch. You snap it in, and the picture is whole. That was the Higgs discovery. It is worth pausing to appreciate what this meant. The standard model of particle physics, the framework that describes nearly everything we observe, was no longer a sketch. It was complete. Not perfect, not final, but whole enough to stand as one of the greatest intellectual achievements in human history. And yet, completion does not mean closure. The discovery of the Higgs did not silence questions. Why does the Higgs field have the strength it does? Why do the W and Z bosons weigh what they weigh? Why is the Higgs boson itself so heavy compared to other particles? Each answer leads to more mysteries, just as every solved chess move reveals new ones still unseen. For now, the mood is one of celebration. The neutral currents observed in the 1970s, the W and Z bosons captured in the 1980s, and the Higgs boson revealed in 2012 together form a narrative arc of triumph. It is a reminder that physics is not only about cold numbers and equations, but also about patience, collaboration, and the quiet persistence of human curiosity. As you drift tonight, perhaps imagine yourself as part of that collaboration, watching a detector screen flicker, hoping for the signal of a rare particle. Imagine the joy of seeing a faint line on a graph, knowing that it confirms a theory woven over decades. That joy belongs not only to the scientists in white coats, but to all of us, for the universe has shared one more of its secrets. By the mid-20th century, the zoo of particles had become overwhelming. Dozens of hadrons, protons, neutrons, pions, kaons, and many others crowded the charts. They seemed like a chaotic menagerie, each with its own mass, spin, and lifetime. It was hard to believe nature could be so untidy. Surely there had to be a deeper pattern. The breakthrough came with the quark model. Instead of treating protons and neutrons as indivisible, physicists proposed that all hadrons were built from smaller ingredients. These ingredients were quarks, bound together in various combinations. At first there were three kinds: up, down, and strange. Later others were added, but even with just three, the pattern of the zoo suddenly made sense. A proton, for example, could be understood as two up quarks and one down quark. Add their charges, two with plus 2/3 of a unit each and one with minus 1/3, and you arrive at a neat total of +1. A neutron, by contrast, is one up quark and two downs, which combine to 0. Mesons, like the pion, could be explained as a quark paired with an antiquark. The cluttered zoo was reduced to orderly combinations of a few basic building blocks, but soon a new puzzle appeared. The rules of quantum mechanics require that no two identical particles can occupy the same state. If three quarks inside a proton were truly identical, they would violate this principle. Something had to distinguish them. To resolve this, physicists introduced a new property, a hidden label, which they whimsically called colour. Not literal colours like red, green and blue, but symbolic names for an invisible charge. Just as electric charge can be positive or negative, quark colour comes in three types, and just as white light is a blend of red, green and blue, a stable particle like a proton must combine quarks so that the colours cancel into neutrality. This idea of colour solved the puzzle. Three quarks could sit inside a proton because each carried a different colour. Their combination produced a colourless state, allowed by quantum rules. The principle was neat, almost artistic. Quarks always come together to form white objects, never flashing a single colour alone. If this still feels abstract, think of a choir. 3 voices sing different notes, and together they form a single chord. The sound is harmonious, complete, greater than the sum of its parts. If one singer tried to stand alone, the chord would vanish. Quarks are like that. A proton is not one voice, but 3 blended in harmony. The introduction of colour did more than tidy up the rules. It hinted at a new kind of force. If quarks carried colour charge, then just as electric charges attract or repel through photons, quarks must interact through their own carriers. These carriers would become known as gluons, the messengers of the strong force. But even before gluons were fully described, the concept of colour gave physicists a way to make sense of the cluttered zoo. It is humbling to realise that what seemed like an untidy mess of particles was, at its heart, built from a few simple notes. Up and down quarks alone, when combined in threes, account for all protons and neutrons, the very particles that make up atomic nuclei and ultimately the visible matter of the universe. Add a strange quark here and there, and the more exotic hadrons fall into place. The zoo was not random at all. It was a well-ordered menagerie, its patterns waiting for the right key. Still, quarks are unlike anything we can see directly. No experiment has ever caught a single quark in isolation. They always appear confined in groups, wrapped inside hadrons. This strange fact would soon demand its own explanation, leading to the theory of gluons and confinement. But already, with the introduction of colour, physics had taken a profound step. For a moment, let yourself imagine these invisible colours. Not the colours of paint or light, but the quiet labels of quarks, hidden deep inside matter. 3 voices blending into harmony, 3 hues combining into white, 3 partners forming a balance that cannot be broken. You are made of these harmonies. Every atom in your body contains protons and neutrons, each one a trio of quarks locked together by their invisible colours. At the human scale, we rarely think of what keeps matter stable. We feel the firmness of a table, the weight of a stone, the warmth of a body beside us. Yet beneath those sensations lies a deep order. Quarks, with their playful colours, bind into protons and neutrons, which bind into nuclei, which in turn gather electrons to form atoms. Out of those atoms come molecules, cells, and the life you know. The idea that all this richness can be traced to 3 tiny quarks in 3 invisible colours is at once humbling and comforting. The universe builds its wonders the way a composer builds music, from a handful of notes arranged in endless variations. The story of colour does not end here. By giving quarks this hidden property, physicists had also opened the door to the strong force, the mightiest of the interactions, one that binds quarks with an unbreakable grip. To understand that grip, we must listen to the voices of the gluons, the carriers of colour. Their story is next, and it is one of confinement, tension, and surprising freedom in the most unlikely place, at the very heart of matter. Quarks, with their invisible colours, are never left to themselves. They are held together by one of the most extraordinary forces in the universe, the strong interaction. If electromagnetism is the force of light and chemistry, and the weak force is the whisper that shapes the sun, the strong force is the deep, binding glue that holds the very heart of matter together. The carriers of this force are particles called gluons, a name chosen with playful honesty. Just as photons carry the electromagnetic force between charges, gluons carry the strong force between quarks. But there is a crucial difference. Photons are neutral, they do not carry electric charge themselves. Gluons, by contrast, carry colour. They are not just messengers, but participants, tangled in the very game they enforce. To imagine this, Picture siblings playing a game of catch. In electromagnetism, the ball itself is neutral. It does not change colour as it flies. But in the strong force, the ball itself carries colour, so each throw changes not only the players but the ball as well. The game becomes wild, with everyone constantly shifting identities. This is what makes the strong force so rich and so difficult to tame mathematically. One of the strangest properties of the strong force is confinement. No matter how hard we try, we cannot pull a quark out of its group. When high-energy experiments smash protons together, instead of revealing single quarks, new particles are born. The energy of trying to separate them simply creates more quark-antiquark pairs, which bind again into colourless states. The result is that quarks remain forever hidden, confined inside protons, neutrons, and other hadrons. It is like stretching a rubber band. The farther you pull, the tighter it becomes. Try to stretch it too far, and instead of snapping, the band produces new loops, new knots, new bands. The original bond is never broken. At the same time, paradoxically, when quarks are close together, the strong force weakens. This discovery, called asymptotic freedom, revealed that quarks behave almost like free particles when crowded tightly inside a proton. But as they drift apart, the force grows, dragging them back. Think of siblings again. When they are crammed together in a small room, they may seem oddly calm, each retreating into themselves. But give them space and distance, and arguments flare. The farther they try to get from each other, the more fiercely they are pulled back into the same orbit. This behaviour is completely opposite to electromagnetism. Electric charges repel more strongly the closer they are. With quarks, it is the other way around. Their bond slackens at short distances and tightens at long ones. Nature, it seems, likes to invert our expectations. The mathematics that describe this are subtle, involving the theory of quantum chromodynamics. Chromo for colour, dynamics for movement. But in plain words, it is the theory of how quarks and gluons interact, weaving the tight fabric of hadrons. It explains why quarks never appear alone, why gluons form a swirling storm inside every proton, and why the visible universe is so stable. Inside a proton, quarks are never quiet. They dart and jitter, exchanging gluons endlessly. The gluons themselves split into pairs of quarks and antiquarks, which quickly annihilate and reform. The proton is less a rigid ball and more a bubbling cauldron, its contents constantly in motion. And yet, out of this restless sea comes stability, a particle with a definite mass, definite charge, and a lifetime longer than the age of the universe. This picture is difficult to hold because our intuition prefers solidity. We want to imagine marbles in a box. But quarks and gluons resist such images. They are more like threads in a tapestry, always tugging on one another, never fraying into loose ends. One way to feel it is to picture a bungee cord stretched between climbers. Each time one climber moves, the cord tightens or loosens, pulling the others along. No climber can wander away freely, and if you try to cut the cord, the energy released is enough to create new climbers altogether. That is the paradox of confinement. Experiments confirm this not by showing us quarks directly, but by showing what happens when we try to free them. At high-energy colliders, when protons are smashed, sprays of new particles burst outward in narrow jets. These jets are the footprints of quarks that tried to break free but instead gave rise to new bound states. It is as if nature insists that no quark should ever wander alone. There is something poetic in this. Quarks, the deepest ingredients of matter, are never solitary. They exist only in groups, in harmony, their colours blending into neutrality. The strong force is not merely about holding matter together, it is about reminding us that even at the smallest scales, isolation is impossible. As you lie in bed, you can imagine this quiet truth. Every atom in your body contains protons and neutrons. Inside each of those, quarks are bound together by invisible cords of gluons. They are forever dancing, forever exchanging, forever confined. And yet, through this restless storm, stability emerges. The stability that lets stars burn, planets form, and you exist. The strong force is a paradox. Chaos inside, harmony outside. It shows us that sometimes the tightest bonds are the ones we cannot see, the ones that prevent any part from being alone. In this way, quarks and gluons are like voices in a choir or threads in a fabric. Each is restless, each shifting, but together they form the substance of the world. The story of the strong force does not end at confinement. Protons and neutrons themselves, bound by quarks, must also bind together into nuclei, creating the building blocks of atoms. And for that, nature devised another clever trick, a force that reaches across neighbouring protons and neutrons, like packages passed over a fence. That gentle but vital interaction is what we will wander into next. Quarks, bound tightly by gluons, form the protons and neutrons that lie at the heart of every atom. But protons and neutrons are not the end of the story. If each proton and neutron remained isolated, the universe would be little more than a thin soup of hydrogen. Something else must bind these nucleons, protons and neutrons together, into the heavier nuclei that make up helium, carbon, oxygen, and all the elements beyond. That something is the nuclear force, an echo of the strong interaction, reaching just far enough across the boundaries of individual protons and neutrons to hold them together. At first, the puzzle was simple to state. Protons all carry positive electric charge. By the rules of electromagnetism, they should repel one another fiercely. How then can a nucleus like helium, with two protons crammed side by side, exist at all? The answer could not come from electromagnetism. It had to be another force, one that overcame the electric repulsion at close range but faded away at larger distances, leaving atoms stable but not collapsing. The solution was found in the idea of meson exchange. Hideki Yukawa, a Japanese physicist, proposed in the 1930s that protons and neutrons exchange short-lived particles, called mesons, back and forth. Each exchange is like tossing a package over the garden fence to a neighbour. As long as the packages keep moving, the neighbours remain connected. This constant sharing holds the nucleus together, binding the nucleons into one community. In practice, this force is a residual effect of the strong interaction. Quarks inside protons and neutrons are bound by gluons, but the leftover field seeps out, much like the faint scent of a candle that lingers in a room. That leftover binds protons and neutrons to each other. The force is strong enough to counteract the repulsion of their electric charges, but only over distances about the size of a nucleus. Beyond that, it fades almost instantly. You can think of it as a kind of cosmic Velcro. Each proton and neutron carries tiny hooks left over from the gluons inside. When they come close, the hooks catch, holding them together. Pull them apart and the hooks slip free, leaving each particle on its own again. The strength of this force explains why the nucleus is so compact. Protons and neutrons huddle close, pulled inward by the exchange of mesons, balanced delicately against the push of their electric charges. The result is a dense core, millions of times smaller than the atom as a whole, yet containing nearly all of its mass. Without this nuclear glue, the periodic table would collapse. The sun would be nothing but hydrogen. Stars would never fuse heavier elements. The carbon in your body, the oxygen you breathe, the calcium in your bones, all exist because protons and neutrons can cling together inside nuclei. It is worth pausing to appreciate the delicate balance at work. If the nuclear force was slightly weaker, only hydrogen would exist, and chemistry would be a barren science. If it was slightly stronger, nuclei would collapse into dense clusters, and the universe would be unrecognizable. Life depends on this narrow middle ground, tuned by the interplay of quarks, gluons, and mesons. To bring the idea closer, imagine a neighbourhood where each house is a proton or neutron. The families inside, quarks, are bound tightly together, never leaving their homes, But across the fences, neighbours toss small packages. These packages keep the community connected, stop the exchange and the neighbourhood dissolves, continue it, and a stable community forms. That is the nucleus, a community of nucleons held together by the steady exchange of mesons. Experiments confirmed Yukawa's vision. In particle accelerators, mesons like the pion were discovered, with masses exactly in the range he predicted. Their existence proved that the nuclear glue was real, not just an abstraction. The pion is not stable, it decays quickly, but in the instant of its existence it carries the bond from one nucleon to another, like a messenger who runs endlessly between houses. As you drift tonight, consider that inside every atom in your body this quiet exchange is happening. The protons and neutrons in your bones and blood are not locked in silence. They are engaged in a constant dance of passing packages, holding the nucleus together moment by moment. It is invisible, unstoppable, and as old as the stars themselves. When you press your hand against a table, you are touching not just wood and matter, but a network of nuclei, each one a small community of protons and neutrons bound by this force. The solidity you feel is built from invisible exchanges, the tireless work of mesons darting across fences you cannot see. By now, with electromagnetism, the weak force, and the strong force woven into our story, nearly all visible matter can be explained. From the electrons around the nucleus to the protons and neutrons at its heart, from the gluons binding quarks to the mesons binding nucleons, the Standard Model has brought order to the zoo of particles. It is an astonishing achievement, a framework that explains the chemistry of life, the fire of the sun, the solidity of the earth, and the structure of the stars. But even as this triumph unfolds, mysteries remain. Why do some particles weigh more than others? Why does matter exist at all instead of annihilating with antimatter? And what about the invisible majority of the universe, dark matter and dark energy, that the Standard Model cannot explain? Those questions await us. But for now, rest with the thought that your very body is a lattice of nuclei, communities of protons and neutrons, each held together by the quiet passing of meson messengers. You're built on harmony born of exchange, a balance of forces so precise that it allows life itself to flourish. By now, we have wandered through a long journey. We have seen electricity and magnetism joined into light, the weak force whispering through beta decay, the Higgs field giving weight to particles, and the strong force confining quarks into protons and neutrons. Each piece has been a chapter of its own, but physics invites us now to step back and take in the whole picture at once. The Standard Model of particle physics is not simply a catalogue of discoveries. It is a framework that says the universe is woven from a set of fields, 17 in all, that fill space and time. Each field has its own particle, its own ripple, its own voice in the cosmic orchestra. Start with the matter fields. There are 6 kinds of quarks: up and down, strange and charm, bottom and top. The up and down quarks are the foundation of everyday matter, making up protons and neutrons. Strange quarks appear in exotic particles, while charm, bottom and top are heavier relatives, fleeting in our world but essential for the completeness of the pattern. Alongside them are 6 kinds of leptons. The most familiar is the electron, the spark of chemistry and electricity. Then there are its heavier cousins, the muon and the tau, each similar in charge but heavier in mass. Accompanying them are 3 ghostly neutrinos, one paired with each charged lepton. The electron neutrino, the muon neutrino, and the tau neutrino, each barely interacting with matter, streaming through your body by the billions every second. That makes 12 matter particles, 6 quarks, and 6 leptons. But they do not live in silence. They speak to one another through forces, and those forces are carried by another family, the gauge bosons. There is the photon, carrier of electromagnetism, flitting endlessly across the cosmos. There are the gluons, 8 in number, weaving colour charges between quarks. And there are the heavy W and Z bosons, carriers of the weak force, whispering in nuclear decays. That makes 4 types of force carriers, 1 photon, 8 gluons, and the W and Z bosons, for a total of 10. Finally, completing the set, there is the Higgs boson, the ripple of the Higgs field that gives mass to the others. It does not carry a force in the same way, but provides the background that allows particles to settle into their roles. Put them together, 12 matter particles, 4 kinds of force carriers, and the Higgs, 17 in all, 17 fields filling space, 17 voices in the orchestra. To picture this, imagine a stage with 17 musicians. Each has an instrument unlike the others. Some play steady rhythms, some provide deep harmonies, others flash quick notes of light. Alone, each would sound peculiar, incomplete, but together they form a symphony. The Standard Model is like that symphony, every particle with its part, every field contributing to the music of reality. Of course, not every note is heard equally. In everyday life, you encounter mostly the up and down quarks and the electron. These 3 make up the matter around you. Neutrinos pass through unnoticed. The heavier quarks and leptons appear only in rare high-energy moments, and the W and Z bosons decay almost instantly. But even the fleeting notes are part of the score, ensuring the harmony holds. It is tempting to ask, why 17? Why not fewer or more? For now, the answer is that this is the pattern nature has revealed. Each field was uncovered through experiment, each confirmed by evidence. The Standard Model is not an invention but a discovery, the recognition of a pattern already written into the fabric of the cosmos. There is something calming in this. 17 fields may sound like many, but compared to the infinite clutter of the particle zoo, they are a tidy set. They explain nearly everything we see: the atoms of chemistry, the burning of stars, the scattering of light, the solidity of matter. If the universe were a puzzle, these 17 pieces fit together with remarkable precision. Still, as in any orchestra, one can wonder about the conductor. Who keeps the tempo? Who decides why these 17 and not others? Those are questions the Standard Model does not answer, but the music it produces is undeniable. As you rest tonight, you might imagine lying in a concert hall, eyes closed, listening not to strings or woodwinds, but to the quiet hum of the cosmos itself. Quarks playing their chords, leptons offering faint counterpoints, photons shining their endless melody, gluons tying voices together, W and Z bosons whispering, and the Higgs providing the depth. You are part of that music, one pattern among many, carried along by the harmony of fields. The Standard Model is a triumph, but it is also a beginning. For while the orchestra plays with perfect timing, there are still notes missing, melodies we cannot yet hear. Some particles, like neutrinos, seem to slip out of tune, carrying masses the theory cannot explain. The balance of matter and antimatter too remains mysterious, and beyond the visible, dark matter and dark energy loom like silence between the notes, present but unplayed. Yet for all its limits, the Standard Model gives us a remarkable view. 17 fields united in a framework that describes the richness of the universe. From the tiniest quark to the cosmic light of stars, everything is part of this harmony. When scientists speak of the Standard Model, they often do so with a kind of quiet awe. Not because it is complete, everyone knows it is not, but because of how precise it is. Few things in life ever line up perfectly. Even the best clocks drift a little, even the best maps leave out details. But in the realm of particle physics, the Standard Model has made predictions that match experiments to a degree almost beyond belief. One of the most famous examples is the magnetic property of the electron. Every electron behaves like a tiny magnet, tilting slightly as it spins. The Standard Model predicts the exact strength of this magnetism to more than 10 decimal places, and when experiments measure it, the numbers match. Imagine predicting the distance from Earth to the Moon and being right down to the width of a single human hair. That is the kind of precision we're talking about. Another triumph comes from experiments at colliders, where particles are smashed together and the debris is examined. The patterns of decays, the lifetimes of exotic particles, the probabilities of rare events all line up with the theory. Even when the Large Hadron Collider discovered the Higgs boson in 2012, its measured mass was exactly in the range the Standard Model had left open. Time and again, theory and experiment have shaken hands. For scientists, this is a source of deep satisfaction. To find that the rules written on paper match the rules written in the stars is a kind of harmony. It says that our minds, fragile as they are, can trace the logic of the cosmos with accuracy beyond imagination. And yet, even as we celebrate this precision, the puzzles begin to appear. The first concerns the neutrinos. For decades, neutrinos were thought to be massless, forever rushing at the speed of light. But experiments watching them arrive from the sun and from nuclear reactors showed that neutrinos can change their identity, oscillating between flavors as they travel. For that to happen, they must have mass, however tiny. The Standard Model cannot explain those masses. Somewhere, the theory is incomplete. Another puzzle lies in the imbalance between matter and antimatter. According to the rules we know, the Big Bang should have produced equal amounts of both. For every particle of matter, an antiparticle should have appeared. And when they met, they would annihilate, leaving only light behind. If that were the whole story, the universe should now be nothing but radiation, with no atoms, no stars, and no people. Clearly something tipped the balance, favouring matter just enough that the universe could form. But the Standard Model does not explain why. Physicists have also found subtle hints in the way particles violate a principle called CP symmetry, the idea that the laws of physics should look the same if you flip particles into antiparticles and left into right. Some decays of strange and bottom quarks show tiny violations of this symmetry. These are real, measurable effects, but they are not strong enough to explain the vast imbalance we see today. Something else must be at work, hidden beyond the reach of the Standard Model. Then there is the riddle of dark matter. Astronomers watching galaxies spin find that visible matter, the stars and gas, accounts for only a fraction of the mass required to hold them together. The rest must be something unseen, a kind of invisible matter that outweighs the visible by a factor of 5. The Standard Model contains no particle that fits this role. None of the 17 fields can serve as dark matter. It is as if the orchestra is missing an entire section of instruments, unheard yet essential to the harmony. And beyond that lies dark energy, the mysterious pressure that is accelerating the expansion of the universe. It is even stranger, accounting for nearly 70% of the cosmos. Again, the Standard Model has nothing to say. It explains atoms and forces with breathtaking accuracy, but it falls silent on the very destiny of the universe. These puzzles do not diminish the Standard Model's beauty. Instead, they highlight the boundary of its reach. It is like a perfectly tuned watch that keeps time with exquisite accuracy, yet still fails to mark certain days. You marvel at its craftsmanship, but you know something more is needed. Physicists continue to test the model, to push it to its limits. At colliders, they search for deviations in particle behaviour. In underground labs, they hunt for dark matter particles colliding with atoms. In space, they track neutrinos arriving from distant explosions. Each experiment is a question whispered to the universe. Is the Standard Model the whole story, or only part of it? For us, listening in the quiet of the night, it is enough to hold both truths at once, the triumph and the mystery. On the one hand, a theory that predicts the world with precision beyond imagination. On the other, a reminder that vast domains remain unexplained. Neutrino masses, matter's dominance, the invisible scaffolding of dark matter, and the expansive push of dark energy. You are part of this balance. Every atom in your body obeys the standard model, its quarks and electrons dancing in patterns predicted to a dozen decimal places. And yet, your very existence depends on the mysteries it cannot solve. If the universe had not favoured matter over antimatter, if neutrinos did not have the masses they do, if dark matter and dark energy did not shape the cosmos, you would not be here. Precision and puzzles are not contradictions, they are two sides of the same reality. So as you close your eyes, think of that perfectly tuned watch. Its hands sweep with quiet elegance, marking the seconds with flawless rhythm. And yet, on certain days you notice it stumbles, skipping a date, leaving a gap. The standard model is like that, a masterpiece of precision, and at the same time, a gentle reminder that the universe still holds secrets we have yet to uncover. The standard model, with its 17 fields, explains nearly everything we see around us. Atoms, light, the fire of stars, the solidity of matter. Yet astronomers discovered something unsettling when they turned their eyes to the galaxies. The visible universe, as intricate as it seems, is only a small part of the whole. Most of what exists is invisible, silent, yet undeniably present. The first hints came from the way galaxies spin. In the 1970s, Vera Rubin and her colleagues measured the speeds of stars orbiting the centres of galaxies. By Newton's laws, stars farther from the centre should move more slowly, just as planets farther from the sun take longer to circle. But the stars did not slow. They raced around at nearly constant speeds, as if the galaxies contained far more mass than the stars and gas we could see. Something unseen was holding them together, like hidden scaffolding. This invisible mass became known as dark matter. It does not shine or absorb light. It does not interact with the electromagnetism at all. Yet its gravitational pull is undeniable. Without it, galaxies would fly apart, their stars flung into intergalactic space. With it, galaxies hold their shape, spirals and clusters maintained like great cosmic cities, bound by invisible highways. Today, astronomers estimate that dark matter outweighs visible matter by a factor of about 5. For every kilogram of atoms, there are about 5 kilograms of something else, something we cannot see, touch, or capture in a laboratory. The standard model has no particle to fill this role. None of the quarks, leptons, or bosons can explain the shadow mass shaping the galaxies. Think of a house built perfectly, its walls straight, its roof strong. It seems complete. But when the wind blows, you realise the foundation is missing. The house holds together only because of something you cannot see, buried underground. Dark matter is that missing foundation. We do not see it, but without it, the structure of the universe would collapse. And if dark matter were not enough of a mystery, another shadow looms larger still: dark energy. In the late 1990s, 2 teams of astronomers studied distant supernovae, the explosive deaths of massive stars. They expected to find that the expansion of the universe was slowing down, tugged by gravity. Instead, they found the opposite. The universe is not only expanding but accelerating, stretching faster and faster with time. To explain this, scientists invoked a strange, pervasive energy filling all of space: dark energy. Unlike dark matter, which pulls galaxies together with gravity, dark energy pushes space apart. Its effect is gentle on small scales but overwhelming across cosmic distances. It accounts for nearly 70% of the total energy in the universe. Try to picture it. Every cubic metre of space, even the space between your hands, carries a faint pressure. It is too small to notice here, but across billions of light years it adds up, driving galaxies away from one another at ever-increasing speed. Dark energy is perhaps the greatest puzzle in physics today. We do not know what it is, whether it is constant or changing, or whether it hints at new fields, new dimensions, or something stranger still. For now, it is a placeholder name, a reminder that the universe is filled with forces we cannot yet fathom. When you add the numbers, the picture is humbling. The atoms described by the standard model, everything we can see, measure and touch, make up less than 5% of the cosmos. Dark matter accounts for about 25%, and dark energy, the silent driver of expansion, fills the remaining 70%. In other words, the orchestra of 17 fields we know is playing only a small fraction of the cosmic music. Most of the symphony is inaudible, waiting in the shadows. This is not cause for despair. It is an invitation. The mysteries of dark matter and dark energy remind us that science is not finished, that the universe still holds secrets beyond our grasp. Just as the faint double lines of hydrogen once revealed the existence of antimatter, so the motions of galaxies and the glow of supernova hint at new rules waiting to be written. As you rest tonight, you can imagine yourself floating in a darkened sea. Around you drift glowing islands, the stars and galaxies we see. But beneath the waves lies a hidden current, dark matter binding the islands into constellations, and all around, an invisible tide, dark energy, pushes the sea itself to expand. You are carried by forces you cannot feel, yet they shape the entire cosmos. The standard model gave us precision and clarity, but the shadows of dark matter and dark energy whisper that our picture is incomplete. The orchestra is larger, the music deeper, the rules of the chess game richer than we imagined. Somewhere in those shadows may lie the next great unification, the next leap of understanding. For now, we acknowledge them, listen for their echoes, and drift with the knowledge that the universe is both known and unknown, luminous and hidden, simple and profoundly mysterious. The discovery of the Higgs boson in 2012 completed the standard model, but it also brought with it a quiet unease. The Higgs was real, its mass measured at about 130 times heavier than the proton. That matched the theory's predictions, but at the same time it revealed a puzzle so delicate that physicists sometimes call it unnatural. This is the hierarchy problem. To understand it, picture the universe as a vast landscape of scales. At the small end lie the familiar particles, electrons, quarks, photons. At the large end lie cosmic scales, black holes, galaxies, the expansion of space. In between lies the Higgs boson, the particle that gives mass to the others. Its weight sits in an uncomfortable middle ground, balanced as if on the edge of a knife. Why uncomfortable? Because the quantum fields that surround the Higgs try constantly to push its mass higher. Virtual particles flicker around it, tugging at its value, threatening to inflate it to scales billions of times larger than what we observe. And yet the Higgs remains modest in size. It is like a pencil standing perfectly balanced on its tip. You expect it to topple instantly, yet somehow it stays upright for billions of years. This delicate balance feels strange. The standard model can describe it, but it does not explain why the Higgs should be so light compared to the immense scales of gravity and the Planck length, the unimaginably small distance where quantum gravity is expected to take over. Without some hidden mechanism, the Higgs mass seems unnaturally tuned, as though the universe had to adjust its dials with impossible precision. Physicists are not fond of such fine-tuning. They prefer when patterns arise naturally, like harmonies in music. So they began to search for deeper principles that might stabilize the Higgs, preventing its mass from ballooning to absurd levels. One of the most elegant ideas was called supersymmetry. Supersymmetry proposes that every known particle has a partner, a mirror sibling with a different spin. Quarks would have squarks, leptons would have sleptons, the photon would have a heavier cousin called the photino, the gluon a gluino, and so on. These partners would balance the quantum tug-of-war around the Higgs. The pushes from ordinary particles would be cancelled by the pulls from their supersymmetric partners. The result? The Higgs mass remains stable, naturally small without requiring miraculous fine-tuning. For a time, supersymmetry was a favourite. It promised not only to solve the hierarchy problem, but also to provide candidates for dark matter. If the lightest supersymmetric particle were stable, it could linger invisibly in the cosmos, accounting for the missing mass astronomers observe. Supersymmetry was a neat, almost too neat answer, tying together multiple puzzles with a single idea, but the universe has remained quiet. The Large Hadron Collider, which revealed the Higgs boson, has so far found no evidence of supersymmetric partners. No quarks, no gluons, no photons. The theory remains beautiful, but nature has not yet revealed whether it is true. Still, the hierarchy problem remains. If not supersymmetry, then something else must explain the Higgs' delicate balance. Some physicists propose that the Higgs is not fundamental at all but composite, made of smaller parts bound together, like the way protons are built of quarks. Others suggest that extra dimensions of space could provide a natural explanation. Still, others think the universe may simply be fine-tuned, the way a pencil improbably stays upright for longer than expected. Whatever the answer, the hierarchy problem reminds us that our current theories, as precise as they are, cannot be the final word. The Higgs boson, though discovered, is not fully understood. It is not just a particle, but a window into deeper rules we have yet to glimpse. To hold the feeling of this puzzle, imagine once again the pencil balanced on its tip. Day after day, it remains upright against all odds. You check back each morning expecting to find it fallen, and each morning it still stands. At first, you marvel, then you wonder, what hidden support is holding it steady? The Higgs boson is like that pencil. It should have toppled into enormous mass values, but it has not. The hidden support, if it exists, remains to be found. And as you drift tonight, think of how strange it is that your very body depends on this balance. If the Higgs mass were far larger, particles would not acquire the masses they do. Atoms would not form, stars would not shine. The universe would be a sterile place, inhospitable to life. Somehow, delicately, the Higgs sits in the right range, allowing all the richness of the cosmos. Perhaps the hierarchy problem is not a flaw but a gift. Perhaps it is the universe's way of reminding us that even in its precision, mystery remains. We can calculate to 10 decimal places, yet still find ourselves staring at a pencil that refuses to fall. When scientists speak of the Standard Model, they do so with a mixture of pride and restlessness. Pride because it explains so much, nearly everything we see, touch, and measure. Restlessness because it does not yet feel like the final story. The Higgs puzzle, the mysteries of neutrinos, the shadows of dark matter and dark energy, all of these hint that the orchestra of 17 fields may be part of a larger symphony we cannot yet hear. For decades, physicists have dreamt of a grand unification. Just as Maxwell once showed that electricity and magnetism were two sides of a single field, perhaps the strong, weak, and electromagnetic forces are three branches of one deeper force. In this picture, at the unimaginably high energies of the early universe, the three forces were indistinguishable. Only as the cosmos cooled did they split, each taking on its own identity, like a crystal breaking along natural lines. The mathematics of such unification is complex, but the intuition can be softened. Imagine three rivers flowing separately through a landscape. Follow them upstream, closer to their source, and you discover they merge into one mighty river. Grand unified theories, as they are called, imagine that the forces of nature also merge upstream, in the earliest moments after the Big Bang. If such a unification is real, it could explain patterns in the charges of quarks and leptons, and perhaps even the reason matter outweighs antimatter. But experiments have not yet found decisive evidence. Proton decay, one predicted consequence, has never been observed. The dream remains tantalizing, but still just out of reach. Another possible extension lies with neutrinos, these ghostly particles so reluctant to interact, may hold secrets beyond their tiny masses. Some theories suggest the existence of right-handed neutrinos, invisible partners to the left-handed ones we know. If such particles exist, they could help explain why neutrinos are so light, and why the early universe ended up favouring matter over antimatter. Neutrinos might be the quiet key to one of the deepest puzzles of all. Why there is something rather than nothing. Physicists have also imagined entirely new symmetries, deeper than those we've already uncovered. Supersymmetry was one such idea, pairing every particle with a heavier partner. Even though those partners have not yet been seen, the idea remains attractive because it ties together the Higgs problem, dark matter and unification in a single stroke. Other symmetries may yet be waiting, hidden in the folds of mathematics, ready to explain the patterns we observe. And then there are wilder possibilities, extra dimensions of space, curled up so tightly we cannot see them. In some models, our familiar 3 dimensions are just the wide corridors, while other dimensions hide in tiny loops, smaller than an atom, shaping the forces we experience. If this is true, the standard model may be only the surface of a deeper geometry. To imagine this, think of a garden hose viewed from far away. From a distance, it looks like a one-dimensional line. Only when you come closer do you see its circular cross-section. Space itself may be like that, more dimensions than we perceive, hidden until we look closely enough. Each of these extensions is an attempt to fit the mismatched keys into the lock of reality. Some fit partially, turning a little, but never opening the door. Others are elegant on paper but silent in experiments. Still, the search continues, driven by the same longing that once led Faraday to sketch lines of force, Bohr to imagine electrons stepping between rungs, and Dirac to predict antimatter. This longing is not only scientific but deeply human. We are pattern-seeking creatures. We want the world to make sense, to reveal a unity behind its diversity. The standard model is already a triumph of unity, reducing the zoo of particles to a set of fields. But the puzzles beyond it whisper that the unity is incomplete. It is worth remembering that each time physics has unified forces in the past, the step seemed bold and uncertain. Few believed electricity and magnetism could be one. Few imagined the weak and electromagnetic forces would join under the Higgs field. Yet nature has rewarded such daring with truth. Perhaps the next unification too lies waiting, just beyond the reach of our current experiments. For now though, the standard model stands as our best map. Like any map, it is not the territory itself but a guide, simplified and incomplete. It tells us where the mountains and rivers are, but not every detail of the valleys. It shows the roads we know, but perhaps not the hidden paths through the forest. The puzzles, neutrinos, dark matter, dark energy, the Higgs balance, are reminders that the map is still being drawn. As you rest tonight, imagine holding a ring of mismatched keys. Each has its own shape, some with teeth filed down, some with ornate grooves. You try them one by one in a lock. Some fit partially, turning just enough to give hope, but none quite open the door. That is where physics stands now, at the door of deeper understanding, with a heavy ring of keys and the patience to keep trying. It may be years or decades or longer before the lock yields, but the search itself is part of the wonder. Each wrong key teaches us more about the door. Each failed attempt sharpens our sense of what the right key must look like, and one day, perhaps suddenly, the lock will turn, and the door will open to a view of the universe more unified than we can yet imagine. Among the 4 known forces of nature, 3 have been drawn into the standard model. Electromagnetism and the weak force joined hands through the Higgs field. The strong force found its voice in the language of quarks and gluons. But one force remains apart, familiar to every child who has dropped a stone and watched it fall, yet elusive in the deepest equations of physics. That force is gravity. Einstein's general theory of relativity, published in 1915, reimagined gravity not as a pull between objects, but as the bending of space-time itself. Matter tells space how to curve, and curved space tells matter how to move. A planet circling a star is like a marble rolling along the contours of a stretched sheet. A beam of light passing near the sun bends because the space-time it travels through is curved. This picture is breathtakingly successful. It explains the orbit of Mercury, the bending of starlight during eclipses, the slowing of time near massive bodies, and the ripples of gravitational waves first detected a century later by observatories like LIGO. Gravity in Einstein's hands is elegant, geometric, and real, and yet it resists. The Standard Model thrives on the quantum world, where particles are ripples in fields, virtual quanta flicker in and out, and interactions are carried by discrete messengers. Photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force. It is tempting to imagine that gravity too has a quantum carrier, a particle called the graviton. This graviton, if it exists, would be massless like the photon, but spin differently, weaving space-time itself as it travels. The problem arises when we try to combine the rules of quantum mechanics with Einstein's curved space-time. The equations that describe gravitons lead to infinities, mathematical results that simply refuse to settle down. In quantum electrodynamics, such infinities could be tamed by renormalization, reshuffling the numbers until finite predictions emerged. But in gravity, the infinities grow wilder the more we try to control them. It is like trying to balance a set of books where the numbers explode each time you add a column. To hold this in your mind, picture zooming into a woven fabric. From a distance, the pattern is smooth and elegant. But as you lean closer, the threads begin to blur, fray, and overlap in ways the loom never intended. Try to magnify further, and the very idea of a thread begins to break apart. Quantum gravity is like that. At large scales, Einstein's fabric of space-time is smooth and reliable, but zoom into the quantum realm and the equations unravel. The scale where this unraveling becomes undeniable is called the Planck scale, a distance so tiny that if a proton were enlarged to the size of the Earth, the Planck length would still be smaller than a grain of sand. At that scale, the smooth fabric of space-time may give way to something granular, foamy, or woven from loops and strings we cannot yet imagine. But experiments cannot yet touch this frontier. Our colliders are powerful, but nowhere near the energies needed to probe the Planck scale. Our telescopes can see galaxies billions of light years away, but they cannot peek into the froth of space-time at the smallest distances. For now, quantum gravity remains a dream written on chalkboards, a puzzle whose pieces are scattered beyond reach. And so, gravity resists. It stands apart from the unification of the other forces, refusing to be captured by the language of quantum fields. Its beauty in Einstein's equations is unmatched, but its marriage with quantum mechanics is still undone. There is something poetic in this resistance. Gravity is the first force we ever knew, felt in the weight of our bodies, the fall of an apple, the tides of the sea. It is also the last force we have yet to understand fully. Like an old companion who walks silently beside us, it shapes every step yet keeps its secrets hidden. As you rest tonight, you can imagine yourself lying on a great woven sheet, the fabric of space-time itself. Your body makes a tiny dimple in the cloth. The earth makes a deeper curve, the sun deeper still. You roll gently toward the hollows made by heavier bodies, carried not by invisible strings but by the geometry of the sheet itself. It is comforting, smooth, reliable. And yet, if you could lean close enough, if you could shrink yourself down to the tiniest scale, you might see the threads blur, the weave dissolve, the fabric give way to something entirely new. This is the mystery of gravity. It resists not out of spite, but because it may belong to a deeper story. And until we learn how to read that story, we live with the tension of two magnificent truths: quantum mechanics and general relativity, each astonishing, each accurate, but still speaking different languages. One day, perhaps, we will find the grammar that unites them, but for now, gravity waits at the edge of understanding, curving space, guiding planets, shaping galaxies, whispering through waves across the cosmos, yet always resisting the cage of quantum theory. When faced with the stubbornness of gravity, physicists have not given up. They have reached for bold new ideas, each one imaginative, each trying to weave Einstein's curved space-time into the quantum fabric. None are proven, but each offers a glimpse of what the deeper story might be. The most famous of these attempts is string theory. Instead of treating particles as points, string theory imagines them as tiny vibrating filaments, like the strings of a violin, but unimaginably small. Each mode of vibration corresponds to a different particle. One pattern of vibration produces a photon, another produces a quark, still another could produce the graviton, the elusive carrier of gravity. This picture has an elegant beauty. The universe, at its deepest level, might be music. Not music we can hear, but a cosmic symphony of vibrating strings, each note giving rise to the particles and forces we see. But strings require room to vibrate in ways our familiar 3 dimensions cannot provide. The mathematics suggests extra dimensions of space, sometimes as many as 10 or 11, curled up so tightly we do not notice them. Like a garden hose that looks like a simple line from a distance but reveals a circular cross-section, when viewed up close, space itself may have hidden twists and turns too small for us to see. If string theory is right, then the universe is a vast instrument, its notes woven through hidden dimensions. It explains not only why gravity might fit into quantum theory, but also why all the particles seem arranged in families, as if they were harmonics of deeper vibrations. And yet, for all its elegance, string theory has not yet been confirmed. Its predictions lie at scales beyond current experiments, leaving it as a tantalizing melody we cannot yet hear directly. Another path is called loop quantum gravity, where string theory replaces points with strings. Loop theory replaces the smooth fabric of space-time itself with tiny loops. Imagine weaving a cloth, but instead of continuous threads, the weave is made of discrete rings linked together. According to loop quantum gravity, space is not infinitely divisible. At the smallest scale, it is made of finite quanta, tiny loops of geometry. In this picture, the continuum of Einstein's curved space-time gives way to a granular structure, like pixels in a digital image. From far away, the image looks smooth, but up close, it is built from indivisible units. These loops may be the atoms of space itself, forming a network that gives rise to geometry, curvature, and gravity. Loop quantum gravity has the advantage of not requiring extra dimensions. It is a direct attempt to quantize space, to give it discrete building blocks. But like string theory, it has not yet been tested. The loops are far too small to measure with current technology. The idea remains bold but unconfirmed. And then there is an idea so surprising that it sounds almost like science fiction, the holographic principle. This principle suggests that our 3-dimensional universe may be like a projection, a hologram emerging from information written on a distant surface. Just as a flat 2-dimensional screen can project a 3-dimensional movie, perhaps our cosmos is the projection of a deeper reality written on its boundaries. The holographic principle emerged from studying black holes. When matter falls into a black hole, information seems lost. But calculations showed that the amount of information a black hole can hold depends not on its volume, but on the area of its surface. This hinted that information in the universe might be stored on surfaces, not volumes. If true, the entire 3-dimensional world we inhabit may be encoded on a cosmic horizon, like a vast holographic film. The idea is radical, but it offers a potential bridge between quantum theory and gravity. In a holographic world, gravity in 3 dimensions could be equivalent to a quantum field theory in 2. Space itself becomes emergent, rising like an image from the flicker of hidden pixels. To picture this, think of yourself sitting in a theatre. You know the movie on the screen is flat, and yet, with the right projection, it appears 3-dimensional, rich and immersive. The holographic principle suggests that our universe may work the same way, a 3-dimensional reality projected from a deeper 2-dimensional description. None of these ideas, strings, loops or holograms, has yet been proven. Each has passionate advocates, each has elegant mathematics, and each points toward a possible way to tame gravity's resistance. But the truth is, the universe has not yet told us which, if any, of these visions is real. Still, the search is part of the wonder. Science is not only about answers but also about the courage to imagine. To say perhaps the universe is made of vibrating strings or woven loops or holographic projections is not a final claim but an invitation to dream. As you lie in bed tonight, you might picture all 3 possibilities. First, a violin string, vibrating with notes too tiny to hear. Then, a net of loops, glowing softly like a spider's web, each ring a quantum of space. And finally, a luminous screen from which our 3-dimensional world projects like a movie. Whether the truth is one of these or something else entirely, it waits for us in the quiet frontier beyond our reach. For now, gravity resists, but imagination persists. And in that persistence lies the promise that one day, perhaps, the threads of quantum theory and the curves of space-time will be woven into one seamless fabric. In physics, every journey eventually reaches a boundary, a place where the maps we have drawn no longer apply. For the quest to unite quantum theory and gravity, that boundary is marked by a scale so tiny, so extreme, that it feels more like a whisper from the universe than a measurable thing. It is called the Planck scale. The Planck scale is named after Max Planck, the German physicist whose work at the dawn of the 20th century helped launch quantum mechanics. By combining the fundamental constants of nature, the speed of light, Newton's constant of gravity, and Planck's constant from quantum theory, one can form units of length and time that represent the limits of our current understanding. The Planck length is about 10 to the power of minus 35 meters. To give a sense of scale, imagine blowing up a proton until it is the size of the Earth. Even then, the Planck length would be smaller than a single grain of sand on that giant Earth. The Planck time, the shortest meaningful tick of a clock, is the time it takes light to travel one Planck length, about 10 to the power of minus 44 seconds. Beyond these scales, our equations cease to make sense. At the Planck frontier, the smooth fabric of space-time imagined by Einstein may no longer hold. Instead, space could become foamy, jittering with quantum uncertainty. Distances and times might come in discrete quanta, indivisible and grainy like the pixels of a digital image. Geometry itself may be woven from something deeper, something we cannot yet see. This is where string theory, loop quantum gravity, and the holographic principle all hope to shine. Each proposes a way to tame the chaos at the Planck scale, to replace the infinities of quantum gravity with a new structure. But for now, they remain ideas without experimental confirmation, because reaching this frontier is beyond the reach of our technology. To probe the Planck scale directly would require energies 1 trillion times greater than those produced by the Large Hadron Collider. No machine on Earth, or even imagined in the near future, can achieve such conditions. Nature did reach them once, in the earliest moments after the Big Bang, when the universe was smaller than an atom and hotter than any furnace. But that cosmic dawn has long since passed, and the traces it left are faint, buried in the cosmic microwave background or in the distribution of galaxies. This means that for now, the Planck frontier is like a whisper drowned in static. We know it is there, hinted at in the way our equations falter, but we cannot yet hear its voice clearly. The instruments we build, as powerful as they are, cannot tune into that frequency. To imagine this, picture standing on a shoreline listening to the waves. You hear the crash of surf, the rush of wind, the cries of gulls. But somewhere, far below the threshold of your hearing, tiny ripples are tapping against the sand, carrying information you cannot detect. You know they exist because of the patterns left behind, but their sound is lost in the noise. The Planck scale is like that. A rhythm too faint for our ears, a structure too fine for our microscopes. And yet, it matters deeply. For at this scale, the questions that haunt physics may find their answers. Why does gravity resist quantization? Why does the Higgs balance so delicately? Why do black holes store information on their surfaces? The Planck scale may hold the key. It is the place where space-time and quantum fields must meet, where the two great languages of modern physics, general relativity and quantum mechanics, must finally converge into one grammar. For now, we stand outside the frontier, gazing in. We construct thought experiments, build mathematical models, and dream of experiments that might someday listen to the whisper. Perhaps in the echoes of black holes evaporating through Hawking radiation, or in the faint polarization of cosmic microwave light, or in the signals of gravitational waves from the early universe, we may glimpse the signature of Planck-scale physics. But even if the door remains closed, there is something calming about this horizon. It reminds us that science is not finished, that mystery still lives at the edges of knowledge. The universe has revealed much: the spectrum of hydrogen, the ripples of quarks, the existence of the Higgs, the expansion driven by dark energy. But it has not revealed everything. Some puzzles are held in reserve, like treasures hidden in the folds of space, waiting for patient seekers. As you rest tonight, you can picture yourself standing before that horizon. Behind you lies the well-charted world of atoms and stars, forces and fields. Before you lies a fog shimmering with possibilities, strings vibrating, loops weaving, holograms projecting. You cannot yet step into the fog, but you can feel its presence, promising that the story is not over. The Planck frontier is both a barrier and an invitation. A barrier because our experiments cannot reach it. An invitation because our imagination can. And in that space between what we can measure and what we can dream lies the essence of science. The courage to wonder, the patience to wait, and the quiet joy of knowing that the universe still holds secrets. After wandering through the standard model, the Higgs field, quarks, gluons, and even the whispers of dark matter and dark energy, it is tempting to ask, where do we stand? The answer is both humbling and uplifting. We have uncovered rules that explain almost everything we can see and touch. But the final chapter, the ultimate unification, remains unwritten. Think of physics as a long chess game. Centuries ago, humanity barely understood how the pieces moved. Newton taught us the motion of pawns and rooks, the predictable arcs of falling apples and circling planets. Maxwell showed us how bishops could slide across the board. Electricity and magnetism joined as one. Quantum mechanics revealed knights leaping unpredictably, their L-shaped moves echoing uncertainty and probability. The standard model mapped out nearly the whole game, showing us how most of the pieces interact. And yet, the endgame is still unknown. Gravity sits apart, its moves only partly understood. Dark matter and dark energy hover at the edges like mysterious pieces we cannot yet see. The game is almost mapped, but not entirely. The rules we have are astonishing, but they are not complete. This incompleteness might frustrate us, but there is beauty in it. Perfection is rare in life. Recipes are missing ingredients. Stories leave questions unanswered. Songs fade before their final notes resolve. Yet the incompleteness makes them human, alive, open. So too with physics. The Standard Model is the recipe for almost everything, but not quite. It is a map of the cosmos with blank corners, waiting to be filled. The precision we have achieved is breathtaking. Predictions agree with experiments to a dozen decimal places. We can calculate the magnetic property of the electron and watch it match nature, as though the numbers were engraved in the stars. We can describe nuclear reactions that power the sun, explaining the light that warms your face in the morning. We can chart the entire periodic table, predicting which elements are stable, which decay, which fuse in the hearts of stars. That is the triumph of the Standard Model. And yet, neutrinos slip between categories. They have masses that should not exist in the theory as written. The Higgs boson balances precariously, its weight feeling unnatural. The universe contains more matter than antimatter, though our rules predict equality. Galaxies spin with invisible glue, and space itself expands with invisible pressure. These are not small cracks. They are reminders that nature has saved some of her secrets for later. But perhaps that is as it should be. Imagine a novel where every mystery is solved by the final page. It may be satisfying in one sense, but it leaves no room for wonder, no invitation to dream beyond the book. Physics has given us a masterpiece that is astonishingly complete, but with enough gaps to keep us curious. Everyday life is built from this almost. The atoms in your body obey the Standard Model. Their electrons and quarks dancing to rules written with impossible precision. And yet, your very existence depends on the mysteries it cannot yet explain. Why matter survived over antimatter, why dark matter holds galaxies together, why dark energy pushes the cosmos apart. You are alive not only because of what physics knows, but also because of what it does not. Think of cooking with a recipe missing one spice. You make the dish, and it is delicious, nourishing, complete in its own way. But you also sense something more could be added, a flavour not yet tasted. Physics is like that. We savour the dish, grateful for its richness, while knowing there is an ingredient still hidden in the cupboard. Or think of music. A symphony that pauses before its final chord does not fail. It invites you to hum the resolution in your mind. The Standard Model leaves physics with such a pause. We can hear the melody, complete enough to carry beauty, yet unfinished enough to leave space for imagination. This is the beauty of almost. We have mapped the stars, tamed the equations, unified 3 of the 4 forces, discovered the Higgs, confirmed predictions with dizzying precision. And still, gravity resists, neutrinos puzzle, dark matter hides, dark energy expands. It is not failure, it is the universe's way of keeping the story alive. As you rest tonight, you can think of yourself as part of this almost. Your body, your mind, your very breath are explained by the known rules, but your existence also leans on the unknown, the missing chords, the hidden pieces. To live in such a universe is not to be deprived, but to be blessed. To walk in a world that is comprehensible, yet still mysterious enough to inspire wonder. The Standard Model is one of humanity's greatest achievements. It is not everything, but it is almost everything. And in that almost lies the poetry of science, the reminder that knowledge is not an endpoint but a journey, a conversation between curiosity and the cosmos that never truly ends. We've travelled far together, from the first sparks of electromagnetism through the whispers of the weak force, into the storm of quarks and gluons, and out again into the shadows of dark matter and dark energy. Along the way, we have seen how physics explains almost everything, yet leaves space for mystery. Now, as our journey comes to rest, let us gather the threads in a soft, quiet reflection. Think back to where it began, with the idea that particles are not tiny billiard balls, but ripples in invisible fields. That shift in perspective changed everything. Light became the vibration of the electromagnetic field. Electrons and quarks became excitations of their own fields. The Standard Model revealed that reality is not built from solid blocks, but from patterns of waves playing on the hidden fabric of space. Then came unification. Electricity and magnetism were once thought to be separate forces, until Maxwell revealed them as two aspects of a single field. Later, the weak force and electromagnetism, so different in strength and reach, were shown to be branches of one electroweak interaction, distinguished only by the presence of the Higgs field. Each step in unification was like discovering that two rivers, once thought to flow separately, joined upstream as a single current. The strong force, too, found its story. Quarks, with their invisible colours, bound by gluons that carry colour themselves, explained the deep stability of protons and neutrons. Even when smashed apart, quarks never appear alone. Confinement keeps them bound, weaving matter into forms that endure. And beyond them, protons and neutrons passed mesons across their fences, binding nuclei together into the heart of atoms. Out of this chain of ripples and exchanges came the entire visible world. It was a triumph. 17 fields woven into one grand pattern. 6 quarks and 6 leptons, the building blocks of matter. 4 carriers of force, the photon, the gluons, the W and Z bosons, and the Higgs field that gives mass. Together they explain nearly all that we can see, touch, and measure. And yet, the orchestra is not complete. Neutrinos hum their faint notes, hinting at hidden masses. Matter outweighs antimatter for reasons still unknown. Dark matter and dark energy stretch across the cosmos, silent but dominant. Gravity itself, so familiar in daily life, resists the language of quantum fields, curving space-time smoothly in Einstein's equations, but refusing to fit into the quantum framework. The result is a portrait of almost complete, almost unified, almost understood, and in that almost lies the wonder. There is a quiet beauty in incompleteness. A recipe with one missing ingredient makes you wonder what flavour is yet to come. A symphony that pauses before the final chord invites you to hum the resolution yourself. A chess game where most of the rules are known, but the endgame still unfolds, keeps the story alive. Physics is like that. It gives us enough to understand our place, but not so much that mystery disappears. As you rest, you can think of yourself as part of this story. The atoms in your body follow the rules of the Standard Model. They're electrons bound to protons and neutrons. They're quarks bound by colour. Yet your existence also leans on the mysteries. The imbalance of matter over antimatter, the presence of dark matter that holds galaxies together, the gentle push of dark energy that carries space apart. You're both explained and unexplained, both known and unknown, both a fact of physics and a mystery of the cosmos. And so, we end not with finality, but with calm wonder. The universe is a chessboard whose rules we mostly know, but whose final moves are still hidden. It is a recipe almost complete, a symphony that pauses in mid-air, a map with blank spaces left uncharted. We sleep under a sky that is unfinished, and that is part of its beauty. Hello there, and thank you for joining me in this quiet journey. Whether your eyes are still open, or you have drifted into dreams, know that the universe continues its gentle dance. Particles rippling, fields humming, galaxies spinning. If you wish, you may return here again to let the science become a lullaby, the questions a soft background hum. For now, rest easy. Time and space will keep their secrets until tomorrow. And perhaps, one day, we will learn more. But tonight, it is enough to know that you are part of this grand and unfinished story. Sleep peacefully, wherever and whenever you may be.